And so would like to introduce our interim department head. We've had a few changes in the past year. Dr. John Feenstra sitting in the back. He's been here at OSU for over 37 years, I believe. 36 of them over in civil and environmental engineering. So he's walked across Monroe Street and giving a little different flavor, serving as our interim department head. So do you have anything you would like to say?
No, I'll just show it again.
Okay. Well, we've got 5 senior design projects this year. We're going to start out with a project for Charles Machine Works. And with that, I'll turn the lights down and let the students start.
All right, so today my team and I are going to be talking about our project, the Trotton Trailer, and our project involvement with Charles Machine Works. So just a brief introduction about the team. I'm James Collingsworth.
I'm Connor Kay.
I'm Skylar Shepard.
Colton Leach.
Trey Minton.
So just a little bit about the client. So Charles Machine Works produces various types of equipment such as skid steers, directional drills, trenchers, and vacuum excavators. They were actually founded in 1902 and they're headquartered in Perry, Oklahoma. So the brand name that most of you guys are probably familiar with is Ditch Witch. Well, Ditch Witch is actually a trade name of Charles Machine Works. So for our project, our goal was to instill our core values throughout our design, such as dependability, innovation, and safety.
So our problem statement was our company wanted us to build a device that allows the FX30 trailer to be moved independently without the help of a vehicle. So a little bit about the trailer is I use it for directional cleanup. I use it in commercial and residential areas. And the main thing is I use it for potholing. And if anybody's potholed by hand, it's not any fun. So this device helps out a lot. And nowadays, when you pothole and you have to see the exposed bury line, when you're digging another line to go under it, you have to visually see it.
A little demonstration here of it. So upon meeting with Ditch Witch, they specified a few designs that a few parameters that our design must meet. It must be able to operate on hard surfaces such as concrete, asphalt, and gravel. It's not designed to work on mud or sand. A design should be self-propelled. What we mean by that is the system must be able to drive and steer itself without the use of a standard motorized vehicle. The system must be integrated onto the existing trailer. So for our design, we were given the FX30 vacuum trailer. So our design had to be integrated onto that trailer. The system should be simply engaged and disengaged. This was a big factor for Ditch Witch. They wanted our device to be convenient not only for them, but for their future customers too. Controls need to be operated by remote control. Also another factor of convenience. They didn't want to restrict the proximity of where they're able to use it. And for the top speed, the system should be able to reach between 1 to 1.25 miles per hour, which is essentially a slow walking pace.
So this is a diagram of the FX30 vacuum trailer that we used. You can see in the back over here is the storage tank, then you have the water tank in front of it, hosing, and then the engine, diesel engine up front. With an 800-gallon storage tank in the rear, you could tell that the weight distribution across the trailer would be very uneven, and this caused a lot of problems during our design problem and challenges as well.
So a little bit about the trailer is, as you said before, we had the 800-gallon tank, but there's also another variation, which is the 500-gallon tank. That one loaded only weighs about 10,000 pounds, but the one we had, when it was loaded, it weighed 18,000 pounds. So the engine that comes equipped on this trailer is a Kubota engine. It produces 24.8 horsepower at 3,000 RPM. And the existing hydraulic system on the trailer was it produced 2,500 PSI with a flow rate of 2 gallons per minute. And from the picture, you can see we actually hooked up our own pressure gauge right behind the pump on the trailer, and we read out 2,400 PSI was what we had for the system.
So this is our project breakdown starting from last August. The group started by picking a project and then brainstorming. After meetings with Ditch Witch, we were able to further our design. And late last year, we completed our final design concept. Beginning this year, we started finding materials, and beginning of February, we started fabrication, and then afterwards, we began testing our design.
So while we were in the early brainstorming phases of our design, we wanted to look at some relevant technology that was capable of moving our FX30 vacuum trailer, which led us to look at trailer tugs. So the Hall E trailer tug is capable of towing up to 50,000 pounds or 40,000 pounds with a max tongue weight of up to 15,000 pounds. But what we really liked about this most is the fact that it's able to be controlled via remote control for the drive and steer, which is essentially what we aim to do for our design. So initially we were designing for trailer tugs, but after meeting with Ditch Witch a few times, they actually specified that they in fact did not want a trailer tug because they want our design to be integrated onto their existing trailer.
So we looked up some relevant patents also. This was a lift axle, which is what we based our 3 drop-down axles upon. The importance about this is when it's down, it just redistributes the weight of, or in our case, the trailer. And when it's lifted, you can move it easily down the road and it doesn't cause any problems.
So one of the things we had to accommodate for in our design were trailer regulations. Our design cannot exceed the width of the trailer of 102 inches or add to the length of over 40 feet. It also had to be safe to operate around people and while on the road.
So this is we ended up putting together a free body diagram to figure out where the weight distribution was of the trailer so that way we can design accordingly. And how we ended up doing this is we took the trailer to a local truck scale here in town and we found the weight of the trailer at a few key points, including at the tongue and at both of the wheels, both of the tires, as well as the full trailer weight. And what we did is we designed so we were able to find the center of gravity of the trailer, approximate the center of gravity of the trailer, so that way we could do the free body diagram to figure out where our weights were going to be and how much weight we needed to, how much force we needed to generate. And we ended up designing for the worst possible conditions we could foresee. And at 18,000 pounds, the axles of the trailer could only handle a slope of about 8 degrees before the axle of the trailer itself reaches its rated limit. So we designed our trailer for 18,000 pounds at an 18,000 pounds at an 8-degree slope. And from there, we determined that we needed a normal force of about 4,500 pounds to be able to generate a drive force of about 2,700 pounds. And those forces just have to be applied wherever we have the drive system applied to.
So for our first preliminary design, before we met with Ditch Witch, we came up with a trailer tug. And this was going to be used at the front of the trailer to just pull it around. And after meeting with Ditch Witch, we realized that they were wanting more of something that's integrated into the trailer. And so a couple of reasons that we weren't going to use this tug is that if going up a hill, with the tank in the back of the trailer, the weight distribution would create a lot less traction for our tug at the front. And as well as you would have to place it under the trailer and remove it back into the vehicle when you're not using it. Our second preliminary design is what we move forward with. This is actually a drop-down axle that would be mounted inside the trailer itself. This would go at the back to drive it. And for this idea, you can see here we tried to reenact these would be a telescoping ratchet. And so it would have substantially more torque, but the downfall to it is that you would have to either manually or electronically flip the direction, but that would also give you a safety brake for it not rolling backwards downhill or vice versa.
The complexity of the design is why we did not continue forward with the ratchet mechanism itself.
Yes.
And here we did some preliminary calculations to figure out how we needed to build that drop-down axle. And from that design, we had straight arm approximations. We made the member straight, we made the piston straight to make sharp angles and triangles. And we used a lot of cosine to figure out the geometry. But the intention is to get the support arm as close to vertical as we could. So that way we can shift the weight that's being bared by the system to the arms. So the arms will bear the weight axially as opposed to the pistons having to take the weight. And here, we did some preliminary calculations using distortion energy theory, and we made the straight arm assumption, but we were able to conclude that we could use 3 by 4 by 3/8 rectangular tubing and still get a generous safety factor. But also, in our calculations, we made assumptions that these were straight members. And as represented by the red line on each of those members, the error was substantially higher on the straight member. So we ended up putting a bend in the arm to not only to create geometric clearance for the wheels and the motors and the pistons, but to also reduce the error that we had in our hand calculations versus what we actually foresaw the project bearing. And with trailers that are heavier than what we have, this is not their biggest trailer, but with bigger trailers, the same members could be used, the same arms could be used, but you could still beef up the bend in the arm by welding plates over those joints.
So here was our final preliminary design that we went ahead and used the bent support arms, and we added a separate or 2 cylinders to raise and lower it. Whenever this goes up under the trailer, you can see here that the 2 cylinders are mounting on the back of the main frame of the trailer, and the axle itself is going to be mounted between 2 of the support arms of the trailer. So there's no major modifications to the trailer to add this into an existing trailer. From the start of it, we could either do electric or hydraulic to drive it. We ended up using electric, and for the wheels, we had to use solid rubber wheels that are actually forklift tires. So the forklift tires we used, they're solid rubber and they're 10 inches in height and 6 1/4 wide. They're actually rated for 4,800 pounds apiece.
And the reason we decided to go forward with these wheels is because at that truck scale, we found at the front, approximately where we would have our front wheel would be about 3,300 pounds.
So for the steering of the trailer, we were originally going to use hydraulics to lift and lower it as well as steer it. So you can see here that we never made any major modifications to the trailer itself. So we just added a pin support for it to pivot up and down, and the cylinder would be on this main frame to raise and lower it.
And by this point, we had met with Ditch Witch, and we had concluded that we were going to separate the drive axle into 2 different motors, independently driven. And so, in finding the torque requirements that we needed to be able to generate those forces, the traction forces that we needed, we originally were under the impression that we had an operating pressure of about 1,200 psi. And so, with 1,200 psi and a motor displacement of 24 cubic inches per revolution, we found that the torque that we could generate was about 4,500 pounds. However, with this trailer that we have, we actually figured out that they have an operating pressure of about 2,400 pounds, which gives us twice the torque that we thought we originally had. But this original torque is what we needed to be able to keep that trailer on that 8-degree slope at its maximum weight of 18,000 pounds. So, and the reason we decided to keep the motors with the extra torque is because there's a lot of friction to overcome as far as steering is concerned. So the more torque we can generate, the better chances we have.
So for our final design for the drive axle, we actually split it and did 2 independent motors. And therefore we could place both of these at the back of the trailer and actually steer it from the back of the trailer. And so what we've done here is the hydraulic motor has got a dual sprocket and chain running straight to the shaft. And then we move this cylinder to the center for the clearance of whenever it's pulled all the way up. The tire is actually touching the top of the trailer, so the cylinder is actually mounted over here. Here is a picture of it. It's actually mounted to the trailer, and as you can see, whenever we raised it up, our plan was to barely be off the ground with the tires. But we actually got it to where it does a push-up, and it is about 2 inches off the ground completely. For the front axle, because we can steer it from the back, we went ahead and just went with a crazy wheel for the front. We would like to have had a smaller surface area for the front tire, but because of the weight that the front tire must bear, we had to use the wider tire. Here is a picture of it in SolidWorks of ideally what it would look like whenever we had it manufactured. And as you can see, we made it to where the plate is perpendicular or parallel with the trailer itself.
And something that this picture does not show is that the location of that crazy wheel is directly underneath the motor of the trailer.
So here is the crazy wheel mounted into the trailer, and you can see that that is a 10-inch tire there, so there's only about 5 to 6 inches that it's actually below the main frame of the trailer. So going down the road, it's not going to hit anything. You hit a bump or run over something. And this is in SolidWorks of what ideally we thought it would look like when we got it manufactured, disengaged and engaged. And here we have a short video of the hydraulics raising and lowering. As you can see, the 3 cylinders are in parallel, so it raises and lowers in the path of least resistance. So they do not all go, they all go up at the same time. We would rather that the front one go all the way up, so we should have sequenced them to where the front would be parallel with the main frame, and the back where we could have changed the pressure so that it didn't pick the trailer off the ground if we didn't want it to.
And as part of our design process, we decided to do stress analysis of the parts that we had. On this piece, we have the 2 longest members, the 2 longest C-channels. Those are representative of what's already on the trailer. And what we added were the mounts for the drop-down arms. And we also have the 4 pins where we connect the mounts to the arms. But with the steel that we used, we had a yield strength of 51 KSI, and we applied a generous load of 2,500 pounds per pin to find a max stress of 36 KSI. And with that maximum stress, that gives us a safety factor of 1.4. However, we also need to note that that was a very generous load that we applied at that point, and the weakest point was actually due to some geometry issues, mainly where those cuts are in the long C-channel. It creates very high stress points. And also something that's important to note about this picture is that this is a very exaggerated representation of what the deflection of the member actually would be. And the next part we did the drop-down arms and the motor mount. And we used the same steel, so it's the same yield strength of 51 KSI. And we applied a load of 2,500 pounds across the bottom of the arm, represented by what the force of the ground would enact upon the arms. We also applied a torque of 4,500 pound-inches on the motor mount. We got a max stress of 21 KSI, which gives us a safety factor of 2.4. But the weakest point that we had there was where the motor mount meets the arms. So in practical application, it's a very easy thing to beef up if the need were required. And we also did stress analysis of the front half of our trailer. So here we applied a load of 5,000 pounds in the upward direction, represented by the ground. And we got a max stress of 10.7 KSI, giving us a safety factor of 4.7. Originally, the safety factor was about 0.6 because we were lacking, or between the plates and the mounts on the pin, we were lacking these 2 parts, causing this plate to warp up or to bend inward. So whenever we actually built the deal, we found that it was indeed warping. So we added these in here so that way we could get a generous safety factor. But also by having a very generous safety factor, we also build it to handle unforeseen loads due to, for example, turning. And we also did a stress analysis of the bottom half of that crazy wheel. So we applied the same 5,000 pounds force upward for the ground, but we also applied a side load of 2,000 pounds to simulate the force through the steering. And there we got a max stress of 34 KSI. That gave us a safety factor of 1.5. Originally, and whenever we built this, we found that the weakest point was in fact where this vertical rod meets that flat plate. And we found that plate was warping down on the trailer. So what we ended up doing is we added a second plate of the same 3/8 inch steel, which gave us the actual safety factor is substantially higher than what it was.
So some of the key components used for our design was an Eaton 2000 hydraulic motor, a 2-inch bore 8-inch stroke hydraulic cylinders, a remote and receiver, various valves, and the forklift press-on tires.
So this is the hydraulic diagram that we built for our circuit, or for our trailer. And what we ended up doing is we had two valves, one of which, the first one, number 4, was a two-directional toggle valve that had the cylinders connected in parallel. And between the cylinders and the valve, we had PO checks that would essentially, the PO checks would open up and allow flow of fluid whenever we engage the valve. But whenever we disconnect, or whenever we return the valve to its neutral or closed state, those PO checks would lock the cylinders in whatever position we leave them in. And beyond that valve, we had another manifold that had two directional valves that were connected to the hydraulic motors. And we also had a valve between the motors and this valve to create a lock that would seize the motors whenever those directional valves were not open. And the way those operate were, if the line is pressurized, those lines open up and allow the motor to turn freely. But whenever the valve side of those lines is not pressurized, those locks close and they act as a brake, so to speak, for the motor.
So for the cylinders that we used, Ditch Witch provided us with 3 hydraulic cylinders that are the 2-inch bore and 8-inch stroke, and our max pressure for those was 3,000 psi. And so for the proportional valve that we used, the operating pressure for it was at 4,600 psi, and the hydraulic motors that we used were 24 cubic inch displacement with the operating pressure of 2,250 psi.
And this is the circuit diagram we ended up coming up with for our controller of the hydraulic system. On the right side, we have the tethered input remote, and that remote consists of 2 potentiometers that acted as they gave the measurements required. So each potentiometer would control 2 solenoids, and there's 2 solenoids per directional valve. So one potentiometer would control one directional valve, and the other would control the other directional valve.
So this is the controller that we used. It's an axiomatic quad controller. This controller allows us to control 4 outputs with only 2 inputs. And the black side, as Connor said, is our tethered side where our remote went into, and the gray side went out to our proportional valve. This is the service program that came with the tool. If you can see the yellow line on the top graph right there, 2.5 volts is neutral on our left motor and our left potentiometer on our remote. And when you push it forward, it jumps up to 5 volts, which is full forward. And when it falls down to 0 volts, it's full reverse. And the same thing on the bottom one, the purple line represents the right potentiometer and right hydraulic motor.
And this is the remote we ended up coming up with. Originally in our design, we had just regular knob potentiometers. And aside from one of those knob potentiometers being broken, we decided to go with joysticks instead, because the neutral state of those valves is whenever that input signal is at 2.5 volts. And so whenever, this is also a big safety issue, because whenever, with a toggle switch, or with a knob, if whatever value you leave that knob at is going to be the value that is returned to the motor. So by having the joysticks, what we're doing is we're creating a safety net where if you let go of the remote, those toggles are going to return to the neutral position and shut those valves and break the trailer.
So this is our failure mode analysis page. What the team came up with was that our highest risk priority number would be traction loss and slipping of the trailer. In worst case scenario, if the trailer is sliding, it could cause harm to nearby people or nearby property. Next was a failure of any of the support arms. This would cause the trailer to collapse, and anyone underneath the trailer or around the trailer could be harmed, or any property that the trailer is over could also be damaged.
So for our testing purposes, we wanted to look at our velocity. We did this by running 2 trials to account for variability. We measured out a distance of 20 feet and used a stopwatch for our time. We were able to find that our average velocity was 1.1 mile per hour, which as specified by Ditch Witch fell between the range of 1 to 1.25. We also wanted to test how effective our trailer was able to stop. And as Connor was mentioning, as soon as you release the throttle from forward to neutral, the trailer would actually stop almost instantaneously. But as mentioned, we only tested this on a flat surface. We haven't tested it on an incline or a decline. And also we wanted to just see how much traction we were able to get on grass after a few days after it had rained. And as expected, we weren't able to get very much traction.
Yeah, the reason being is because the trailer, as you would normally operate it, it has 5 points of contact. With the two tandem axles, you have the two tires on each side, as well as the tongue or the jacker where it's hitched. However, with our particular design, because it lifted the trailer up off the ground, we reduced the number of contact points down to 3, which created very high pressure in those points, resulting in the wheels sinking into the ground. And so from testing, we were able to draw a few conclusions about our design process. And one thing we found is that the location of the motor, it resulted in a very disproportionate amount of weight over the front crazy wheel, and also with us lifting the back end of the trailer off the ground, we shifted more of the center of gravity of the trailer forward as well. And what this ended up doing is that front crazy wheel, the rubber on the tire, compressed substantially, and it resulted in a very large footprint that gave us a lot of resistance whenever we tried to turn. So the turning resistance was in many cases higher than the turning force we could generate by the drive motors. That's not to say that the trailer can't turn, but it's a very finicky process, and it takes a lot of moving around to get it to actually turn where you need it to. And some of the solutions we were able to come up with to solve this problem, we found that we figured we had enough displacement on the hydraulic motors that we had, but the problem was we were having a difficult time generating the right amount of torque. So one solution to this would be to increase the pressure that those motors have. And so if we replace the hydraulic pump on the trailer with more pressure, we could get higher turning torque. And some of the other solutions we had included adding an additional crazy wheel in the front that would be able to split the weight. And with the weight reduced per tire on the front, we could have a smaller tire, so to speak, and reduce the amount of turning friction that those tires generate. And we also, along the lines of that idea, we could also add hydraulic motors to those front crazy wheels to help them pull themselves along as well. And something else we could have done would be to add a servo motor to assist in the steering of that front crazy wheel. And something else that we attempted to do was we attempted to find room to fit in a gear reducer, a gearbox that would be able to generate more torque given the hydraulic pump that's already on there. But for simplicity and the design's sake, we decided to keep everything in line. And
So I just wanted to say special thanks to Richard and everybody at Charles Machine Works for donating all the materials along with helping us fabricate all our parts. And Travis Peterson, who donated the proportional valve to us, as well as Wayne and everybody in the BAE lab that helped with our putting everything together. And then also Dr. Weckler, Dr. Long, and Dr. Wang.
do we have any questions?
Questions for this team?
What was your ground clearance when everything was folded up? In other words, what was the minimum or what was the riskiest area?
The minimum on the rear was the kind of limiting factor of it. We were just about 1.5 to 2 inches below the rear axles, the tandem axles. So for them to touch the trailer, the back of the trailer would have to be touching the ground as well. And it will, if you back up to a curve with it, the drive tires are actually about 6 inches behind the rear axle tires. And so it would, if it's a tall curve, it would hit them first, but a normal size curve, it will just kind of be over the top of them and it won't hit.
If you were going downhill, is there any concern about trailer running away? Did you have any brake?
Yes, that would also be something that we would actually design for as well, is on the remote, something that we would like to do is put in a logic function that if the valves are open, then have a brake, or something that connects to the trailer's brakes, or turn off that brake, but whenever the valves are closed, that brake will engage. That would be something I'd looking at, but for our purposes, the braking function of the hydraulic motors and the PO check valves that we had was sufficient. Yeah.
Earlier, we were comparing the straight beam for the supports for the wheels and the end piece. You said you had given a generous safety factor. What was that generous safety factor?
Most of my stuff I tried to design for around a safety factor between 2.5 to 3. And the reason is because with something that weighs 18,000 pounds, you don't want anything breaking and going wrong and potentially injuring somebody. So we generally try to aim for around 2.5 to 3.
What kind of configuration changes would you have to make to run this on non-asphalt, non-concrete surfaces?
We would, or the main thing we would have to do is, a major problem we have, I guess, is the torque that we need to turn it. So that's one issue in and of itself. But whenever we had the trailer sinking into the ground and whatnot, that was because we had so much weight on 3 relatively small areas. So ideally, what we could do is also, if we could control how far those rear arms extend downward, we could keep the tandem tires that are already on the trailer, we could keep those in contact as well and have 4 additional contact points to help spread out the weight and keep us from sinking in the ground. But aside from that, we also, a design change we're also contemplating would be to change the frame, I guess, and this is just theoretical, I guess, change the way the deck is built, so that way we could accommodate larger tires and increase the surface area and possibly get better traction out of those, because these are also ball tires just because of the weight that they have. Yeah.
Did you give any consideration to how this would behave on a side slope?
So the way we did that is, or like we were saying, the intention was originally to have the tandem axles in contact with the ground as well. So in an ideal situation, we would be able to.
We would make the rear to where you could apply just enough pressure to just barely to take weight off of the trailer, so we had enough traction to drive it.
And
so you would have the actual tandem axle tires to be able to help support yourself on a trailer or on a slope.
Yeah. And so if the trailer itself, I guess, without these drop-down axles engaged, can keep from toppling over, I guess that would be what we would expect on here as well. However, with the way we have it set up now, there's no feasible way we could steer it on a slope like that. But that's because the steering mechanism will need to be redesigned if this process goes forward. So.
On your speeds for the forward and backward, is it basically a fully open or is it a modulating valve? So is it constant speed or?
So they're proportional valves. So it's not it's not all or nothing. It will open partially if you yeah.
And then it looked like on your speed tests that your average speed was higher than your 2 trials. Was that just a rounding error?
Go back to the, I converted. Yeah, that was a feet per second. Minutes mile per hour, I just averaged those 2.
So is that just a rounding error?
Yes.
I guess? Yeah.
Any other questions for this group? Well, they will be driving this around the parking lot over at the Biosystems lab later this afternoon. So let's give this group a round of applause. And if you could fill out the evaluation while the next team gets prepared. We use these for our engineering accreditation assessment. Anybody else need an evaluation? Yeah. Well, just as a side note, starting next year, we will have a new class required for all our mechanical machinery students in off-road vehicle and ag machinery engineering that Dr. Long is going to teach. It will be a required class for that option, and there will be a fair amount of traction mechanics in it. Sort of like the good old days, right, Joe and Kelvin? It's been a long time since we've taught traction concepts. Okay, I don't see our other team. Are you guys good? Okay. Well, we're doing a lot of new things this year. For the first time ever, we have included as part of senior design the ASABE quarter scale tractor pull competition as one of the senior design projects. We're probably one of the last universities in the country that haven't included quarter scale tractor as a segment or a part of senior design. Many other universities for years and years have been doing quarter scale as a senior design project. So at the end of last year's quarter scale competition, Dr. Long, who's the team advisor, talked with me, and we talked about the idea of including quarter scale as a senior design project and how it could still fit the educational objectives that we need to accomplish in senior design, especially to meet the ABET requirements. So with that, I'll turn it over to the quarter scale team.
Like Dr. Wickler said, we're the Cowboy Motorsports Senior Design Group. I'm Garrett Dollins.
I'm Scott Dick.
I'm Logan Gary. So as Dr. Wickler talked about, we participate in an annual design competition sponsored by ASABE, also known as the American Society of Agricultural and Biological Engineers. They're a big sponsor of the competition, as well as many big names industries such as Caterpillar, John Deere, NAGCO. About 30 teams, including national and some international teams, participate in the yearly competition. So the competition, we take part in, it's a design competition. So we have a report, we have a presentation, we do some design judging where they judge on base of how well we designed our tractor, as well as how well we can present the tractor as a production piece. And we also have a pull requirement, a maneuverability requirement, and a durability event, where we basically test the tractor and show that it performs as we designed it. So our goal was to design and build a cost-effective, reliable, and innovative frame, steering system, and suspension system for the team. Design will take into account the team's budget, our timeline, and our resources available that we raised in the previous year.
So the first part of the tractor we're going to look at is the frame. These first two requirements here are kind of just what a frame is, kind of the definition of a frame. So our frame needs to withstand the weight of the tractor and forces felt during competition, and it has to give area to mount other components of the tractor onto it. The last two requirements are the only two requirements given in the rules for quarter scale tractor competition. It says that the frame has to be less than 96 inches long, and it has to be fully customized. This means we can't take a frame off of a lawnmower or a lawn tractor and use it as our own. We have to design our own frame from scratch and use our own design. So when we started talking to the club about what they wanted us to do with the frame, we came up with some more precise objectives. They told us they wanted it to be easily manufactured. Like Logan was saying earlier, manufacturability has a point value in the design judging. So the easier manufactured it is, the more points you'll get. They also wanted the frame to be fully welded together. Making it fully welded together increases its strength, makes it more durable. They wanted the frame to be as lightweight as possible, but still be strong enough to support the weight of the tractor. Since the tractor has a weight limit, it's very important to keep everything as lightweight as possible, but still functional. This last one, they wanted the frame to display the school name and the club name in some way along the frame rails. So when we started deciding on what type of frame we wanted to use, we didn't want to just use last year's frame design just because that's what we had been using. We wanted to start from a clean slate and make sure we could use the right frame selection for our application. So we started looking at what different types of frames you see in industry. The ones we found here were the tube frame, the unibody frame, and the C-channel frame. The tube frame is what you mostly see in heavy duty and off-road equipment like semis and tractors and things like that. It's a very strong frame. It's able to support the weight of the machine, and we're able to put through a lot of abuse. The only backside to that is it's a little bit heavy. It's a little bit too heavy for our application, and we don't exactly need all of the strength that it gives. So we did not go with the tube frame. The next one we saw was the unibody frame. You see this mostly in mass-produced cars. It's a very economical way to do it. Most of the major components are just bolted on. It requires a lot of precise engineering and manufacturing. We were not exactly provided with the type of manufacturing needs that we would need to do this type of system. But we like the idea of being able to bolt on major components. Like I said earlier, that's a manufacturability kind of thing where we can do better in that way and gain points in the design competition. We also like the idea of the whole frame being one unit, and we can spread forces out throughout the frame whenever it's all connected. So even though we would not be able to do this type of frame, we wanted to keep in mind the ideas of the unibody frame that we can apply to our own. This last one is the C-channel frame. It's like a tube frame except missing one of the side flanges. So as you can imagine, it's a little bit weaker, but it makes it a little bit more lightweight. It is strong enough to support the tractor that we will be building if we give it the right support structures, and it's a lightweight enough frame. So this is the type of frame that we went with. Like I said, it's a lightweight system, and we have used it in past years, so it's a proven system. We know how it reacts to different forces of competition. We know some of the weak points where we need to add different supports. So that's one way we can improve on that. We also decided to make it easily manufactured. One way we're doing this is by implementing the slot and tab method. As you can see on the picture, slot and tab method is where you give the piece you want to mount some tabs and then cut holes in the piece that the other piece is being mounted on, so that it can easily slide in there without any measuring or other measurements like that. This makes manufacturability a lot better. It's a lot faster on the fabrication side because, like I said, there's no need for measuring. The human error side of it is out of the equation because the holes are already pre-cut and you don't have to measure anything. It also makes it easier to weld because all you have to do is slide the piece into the hole and then tack it in. And then with all these, with all the slot and tab stuff, everything will be able to be, major components will be able to be bolted on into the mounting tabs that were welded onto the frame. Since we were going with the C-channel frame, we could look at our previous design and kind of see what needed to be improved. Here's some specifications of what the previous design had. It was made out of 14 gauge steel, which is 0.0747 inches. It was 5 inches tall. The top and bottom flanges were 1 inch, 17 inches wide, 91 inches long. The bends right before the rear diff mount were 45-degree bends, and everything was bolted together. There wasn't anything welded on that frame, and there was also no additional support structures designed into this system. Since there were no support structures designed into it, you can see in this picture there was some good cracking that happened at the top and bottom of the frame at those 45-degree bends right before the rear differential mount. This was due to the fact that we forgot to weld the frame at the bins after it was bent for us by Ditch Witch. We should have welded the pieces in there and it would have strengthened it up. But hindsight is 20/20. But the cracks happened because, as you will hear about in a little bit, the suspension was solid. So whenever the tractor would go over a bump, the frame had to absorb all of the shock from that. And so when the rear tires would torque a little bit, all the stress caused by that would go right to those cracks, and it was released through by cracking the frame. To help combat the stress concentrations there, those 45-degree bends, for the new design, we changed the 45 degrees down to 30 degrees. As you can see in the SolidWorks simulation that we did on these pieces, there's a lot less stress in the 30-degree bends. There's a lot of stress along the bend here on 45, and you can see even a little bit more right in the bend as compared to what is seen by the 30 degrees. It is less in the 30-degree bends because whenever a force acts along the flange of the frame, more of the force is transferred down the length of the frame instead of perpendicular to it, which was what caused the cracks in last year's frame. To further strengthen the rear end, we added some cross members and supports right around the weak point at those bends. We put one support right before the bends, as you can see in the SolidWorks model, and then another one at the very end of the frame to box in that weak point and further strengthen it. Since we boxed in the rear end, we had to redesign the rear differential mount. We ended up making it better and easier manufactured by making it to bolt onto the end of the frame instead of sliding in like the other one did. This makes it easier to do maintenance on the rear end because by undoing the 6 bolts that hold the rear end to the frame, you can successfully split the tractor. It also helps with manufacturability because the rear end can be built as a subassembly and then bolted on later on in production whenever it is whenever the frame is complete and it's ready to be put on. So the next place we looked at, or the next place we found that was a failure on last year's frame was at the front axles. Like I said, there was no support structures designed into it. And so the frame actually the top wanted to bend in toward itself, and the bottom wanted to spread apart whenever the weight of the tractor, the tractor's weight was sitting on the frame. So at competition, they noticed that the frame was twisting in on itself, and they had to quit welding some straps along the bottom to keep it from doing that, to keep the frame together. So for our new design, we incorporated the same idea. The A-arm mounts are now part of the support structure. It runs from one frame rail to the other to keep the frame together and keep it from splitting, from torquing in on itself. Once we decided on all of the support structures, we started looking at the shape of the frame rail itself. The first one we came up with was what we call the wide engine frame. You can see it's wider at the front where the engine would sit. We did this so that we could lower the engine to lower our center of gravity. This ended up causing problems down the line with drivetrain and transmission and other mounting of that stuff. It ended up causing more problems than it solved, so we did not go with this system. The next one we came up with was what we call the short frame. You can see it's very skinny. We did this to make it more lightweight. It wasn't quite as strong as other designs we came up with, but with the right support structures, we thought it would be able to work. Unfortunately, it did not. It was not compatible with our new front axle design, so we had to modify it, and we eventually came up with this frame rail, and it's a little bit wider around the front axle to accommodate the new front axle design. We put it under a SolidWorks simulation of about twice the amount of data we see at any time during competition. You can see it was very strong underneath these forces. There's a little bit of stress concentrations here at the ends. That's because of how it was mounted in SolidWorks. You have to set parameters, and those forces will not be seen whenever it's actually mounted on the tractor. A little bit about this frame rail. It is 14 gauge steel. We decided on 14 gauge because last year's frame was just 14 gauge and it ended up cracking, but it didn't have support structures. So this year's frame, we decided we could go with 14 gauge again and avoid the cracking by putting in more support structures. Once we had all the pieces completed, we started putting them together in SolidWorks to see how they would look together and how everything would fit, also to see how it would react underneath certain forces. The main change we did as compared to last year's frame was we reduced the width from 17 inches down to 14.5 inches. This made each cross member 2.5 inches shorter, which made everything lighter when compared to last year's tractor, if it would have been 17 inches. After everything was put together, we ran a simulation on the whole assembly to see how it would react to the forces felt during competition. You can see most of it is blue, the color down here, which means that it is very strong and will withstand those forces that it would see. Once all the pieces were designed, we sent all the drawings off to Ditch Witch to be cut and bent for us. They graciously donated all the material for it. Once we had all the pieces, we gave them to the BAE lab personnel to weld up for us. It ended up being 27 total pieces that were part of the frame that are now one piece after they've been welded together. It took the guys in the BAE lab about a little over a day to complete it, and they actually complimented our slot and tab design and said it made it a lot easier and a lot faster to put the frame together. After the frame was completed and welded together, we did some very unscientific tests on it. We wanted to see just how it would react to some basic torsion tests. So we clamped one end of the frame down, and a team member stood on the other side and twisted it back and forth to see how much force it would take to twist the frame. And based on our memory of how last year's frame reacted under the same forces, this year's frame was a lot stiffer, and we were very satisfied with how it reacted to those forces. We will do much more observations and some testing whenever the whole tractor is complete and we are able to do some test polls. We will like to watch and see how the frame, where it moves around and how it needs to be strengthened, to see if there's anything we need to add to it. And a successful frame will be a design that will have no deformities or failures. So we're trying to avoid what happened last year with these big cracks in the top and bottom.
Alright, so the next component of our design was to design a new steering system for our tractor. So the goals that we set forth for ourselves and were given to us by the club was it had to be a usable system, had to be adjustable for various operators, it had to be reliable, so required minimal maintenance, which also meant it had to be low maintenance. So last year's design, which you can see up on the screen, it was pretty simple and straightforward. It was just a drive shaft straight into a rack and pinion, which then attached straight to the steering knuckles on the tires. So it was very easy to manufacture, it was very few components. It was simple and it was very lightweight. But with these strengths, it also came with some weaknesses. It was a straight 1-to-1 ratio, so however much force it required to turn the tire on the ground was how much force we had to put into the steering wheel at the operator end. This also resulted in very poor turning radius, as you had to struggle to turn the steering wheel so you couldn't actually get into a complete turn. We also came across a toe alignment problem while designing this year's suspension. So you can see on the left side of the screen, the air spring is fully inflated in the driving position. Your tire is straight on as it should be. but when we lowered it down to a pull position, we found that the tires were getting pushed out into a toe-out position. So we decided we need to look into this some more. We did some background research with the Ackerman steering geometry and parallel set steering geometry. So in the top picture, you can see the Ackerman steering geometry, where each tire turns a different amount. The inner tire turns a bit more than the outer tire, as it has a tighter circle it needs to maintain to keep concentric circles to make a good turning radius. Your parallel set is when the tires turn in the exact same direction, so you're fighting yourself as you go through a turn. So with this year's steering design, we decided to keep the rack and pinion system from previous years, as the club's very familiar with its workings. We have a bunch laying around to test on the tractor and test different mechanical linkages. We also decided to use some chromoly turnbuckles. As we found the previous year, these are very strong, very durable, and they're very lightweight, since we do have a weight requirement for the tractor. We also added an inline gear reduction, which reduced the steering effort by half compared to the previous year. We also added the larger steering wheel, which also aids in our turning effort and steering. We also improved the geometry from a straight parallel set to a more close to a Ackerman steering design. So you can see the pictures above. Here's the assembled steering from this year's design. So on the right side of your screen, you'll see that the rack and pinion is straight in line with the steering knuckles, and the turnbuckles are almost perfectly parallel to the ground. This allows us to transfer all the forces going through the rack and pinion to our tire, so we don't lose anything through an angle like we saw in the previous year's design. We also decided to move the steering knuckles below the tractor, so we're not fighting ourselves when we raise and lower the tractor, to help solve the toe-in, toe-out problem. So we've been doing some testing, and we have still further testing to do, but we noticed that the gear reduction significantly reduces the force required to turn the steering wheel. As the tractor nears completion, when we get some test pulls in, we will also see how well it handles underneath pulling conditions, as well as just driving around open field. And we reached our design goal of reducing the overall steering effort of the tractor.
So for the suspension aspect of the senior design, our group and the Cowboy Motorsports Club sat down and set two main objectives. The first objective is we wanted to have an adjustable ride height. And the second objective is to improve the ride quality of the tractor for the operator. The first objective is because when we're pulling, we want to have the tractor in the center of gravity as low as possible. But during competition, we have other events, such as this is the durability event, where we need to be able to raise it up so that we don't have any clearance issues. And also for doing tech-in, we have to be able to drive up on scales and the brake stand here. So having the adjustable ride height really helps with maneuvering around. And the improved ride quality is mainly just for the operator and to reduce the amount of stresses that the frame sees. So the previous year's design was just a totally rigid system. It had a couple of advantages. It was very lightweight and it was adjustable. However, the adjustability was limited by thread links, so it wasn't a large amount of adjustability. And then there was also no articulation and no damping action going on. So we decided to start with a blank slate because we didn't have any suspension before, and we looked at 5 different systems that were a possibility. These are coilover shocks, linear actuators, hydraulic cylinders, air shocks, and air springs. 2 of these were thrown out because they could not meet the 2 main objectives that our group set. So we were left with hydraulic cylinders, air shocks, and the air springs. Then we set a decision matrix based off of these criteria: cost, weight, strength, pulling performance, durability, adjustability, and ride quality. Each of these criteria were given a certain percentage value. This was based off of what's most important during the competition, and then from that, each of the concepts we had were given a point value from 1 to 3 based off how they would perform, and we ended up seeing that the air springs overall were the best choice for our project. Testing. So we took last year's tractor last semester and had some air springs that we put on it. We went through 3 different iterations before we had a working prototype. Initially, we discovered that the air springs that we had were not sized properly and could not lift the weight of a fully ballasted tractor. To compensate for this, we tried to move them out more to be able to get more of a lever arm to see if they could actually lift the tractor. Then we ran into a few clearance issues. Once we got that worked out, then we had a working prototype. And here's the picture of what it looked like when we got it all sorted out. And here's a video of last year's tractor with the new suspension. So as you can see here, it does raise the nose of the tractor like we want. However, there's that major toe in and toe out issue that Logan was talking about before. So for this semester, I wanted to make sure that we had the proper size air springs selected so that it could handle all of the weight that the tractor would see during competition. So if you look at the top A-arm and treat it as a simple beam, here's a diagram of all the forces and reactions that it sees and the different variables that we can change, such as the center distance from the air spring to the pivot points, how big the air spring is itself, and how much clearance we want to have between it and the tire so that we can make sure that no rubbing occurs. Using this, we decided to look at 3 different air springs, and we came up with, we decided on this middle one here, and it has a safety factor of 1.23. This is high enough because there's no danger to the operator if something were to fail during the system. You cannot lose controllability. There are safety bump stops installed and other safety interlocks that will keep you safe. So their safety factor of 1.23 is plenty for this project. And this picture on the left here is the pneumatic system that runs the airbags and the air compressor that we have. And then on the right you can see this is initial fabrication of the A-arms, and here we're just testing to make sure that the linkages and how the A-arms move up and down are as we designed. A few more pictures. This is with most of the suspension put on, and then here in the picture on your right you can see these are scales that we have. So we zeroed them, loaded the tractor on them, and then weighted it up to 1,500 pounds, which is the max amount of weight we're allowed to have during pulls, and then cycled the suspension about 5 times to make sure that everything was working properly, and it worked really good. Here's another video of the new tractor and the new suspension. Raising. So in this video you can see that initially from the very nose of the tractor down to the ground is about 5 inches, and then when it's in its fully raised position that's at 17. So that is plenty of ground clearance for any kind of anything that the tractor will need to do during competition. A-arm design. The A-arms were designed with 1-inch chromoly tubing. It's a super lightweight material. It's very, very strong. It's great for this application. We knew this from last year's design. It included it, but we needed to do a few updates to it as far as serviceability and manufacturability goes. So a few places where we worked on them is where the ball joint tab slides or is connected to the A-arm itself. This is last year's picture on the left. Being able to weld this surface is difficult, so instead we made it where you could slide the tab in and it gives you more welding surface all around, so it's stronger and it actually uses less half-inch plate material. And then here you can see this was another after-the-fact modification to last year's tractor when the frame was bending in on itself. So now the tabs that are right here, this is all one piece that's been welded together. This is a diagram of the pneumatic system that actually controls the air spring system that I showed you earlier. Number 1 and 2 are the valves that are used. Number 4 is a quick disconnect. So the system is separated into an upper and lower half. In the upper half, if you want to, there's a switch up by the air compressor. You can press it and it breaks contact to the switch on the dash that controls your ride height adjustment. And then it also kicks the pump on and pressurizes it up to 150 psi so you can fill the tires on the tractor or fill an auxiliary tank for other uses. And then in the lower lower section of the system design, here is a pop-off valve to protect it. The air springs are rated at 100 psi, so that pop-off valve is 90 psi to protect it. And then here is a Schrader valve. So let's say you have a failure on your air compressor. If it goes down, you can bring an outside air source in and still be able to inflate the air springs to be able to maneuver around. And then here's the electrical diagram that controls it. As you can see here, the double relay is what breaks contact between the auxiliary switch, and then this is your ride height control switch that's up on the dash. This is a safety interlock so that if the operator gets off and wants to fill the tank, if someone else is around and they accidentally hit that switch, there's no possibility of a pinch hazard or danger to the operator that is trying to use the auxiliary fill port there with the moving suspension components. Here's a cost breakdown of everything that we did for our senior design project. It's broken down into 2 different ways. The top table, as you can see, this is broken down into material costs, fabrication, labor, and then purchase parts. Obviously, the purchase parts was significantly more than everything else. Like I said before, we've designed to lower the material cost, the fabrication, and the labor cost, and so I think we were pretty successful in that. And then on the bottom, this is broken down into the 3 different components. We worked on the suspension, steering, and frame, and so there's a price breakdown on that as well.
So another component to the design competition that ASABE puts on is analysis of your design through a failure mode analysis. So we decided to do one for our design systems of the suspension, the steering, and the frame. And so we basically went through as a group and thought of everything that could possibly go wrong with our tractor, wrote it all down, and then using the FEMA analysis, we found that everything was below the risk priority number, or RPN, that is known as 99, which is given out by ASABE in the competition rules. So we figured that all of our designs met and exceeded the requirements given to us. Another part of senior design that we want to talk about is we like to involve our freshmen in our projects. So we had 2 freshman groups we worked with. One group decided to help us design a rear differential mount. So on the right, you can see what they ended up coming up with, which had some similarities to what we came up with as a group. We also had another group help us design the mounting bracket for our transmission, as it's a strange shape, and it allowed them to learn some on how to use SolidWorks and to measure properly.
So before competition, obviously their tractor is not completely finished yet. What we have left is to finalize all the fabrication. We need to do some testing. We'll take the tractor out once it's completed and do some test pulls, and then also some durability testing, and then after that we'll blow the tractor apart, paint it, and then load it and head to Peoria, Illinois. Thank you for your time. Are there any questions?
On your frame design, were you able to maintain or decrease the weight of the frame this year versus last year?
It's actually a little heavier than what last year's was, mainly because all the support structure is designed into it. We were willing to take an increase in weight to maintain usability, so it is actually a little heavier.
Earlier in the presentation, you said that last year's had some issues with turning radius. With the improved steering design, what do you improve that from to?
Hasn't been measured yet, but once the tractor gets running, we'll get to measure how well it turns in comparison to last year. Last year didn't really have much of a turning radius. It kind of went forward and moved sideways if you wanted it to.
Is that, that logo that says on the frame body, it says Cowboy Motorsports, does that weaken the frame to any degree, or did you do any calculations on the?
In that area, there's not a lot of stress. Most of the stress is at the front axle and at the rear end where we boxed it in. So right there is not a whole lot of stress. I did some SolidWorks simulations with some of the letters in there. I didn't show them all up there, but there wasn't a whole lot of stress concentrations around those corners like you would think. So it doesn't affect it much in that area.
You said you had a gear reduction to try to make it easier to turn. You know how many turns you've added? Try to go from right to left.
It went from 1 turn to 2, so it was just a 1 to 2
So you have twice as many turns. And you think you'll be able to get through your maneuverability.
Yes.
So you kids seem to be working independently. Is there a group amongst you that coordinates the various components going in lots of different directions? Or do you pretty much bolt them together and then find the issues you need to solve afterwards?
No, we definitely work together. So us 3 and then the rest of Cowboy Motorsports that does the drivetrain, designs the exhaust, the operator station, all of that, we work together constantly. We don't have an officially appointed head of that, but I have acted as that, and then also the other members. We're a good team, and so we're constantly around each other, and so yes, there's lots of communication that goes on with that. The full tractor was designed in SolidWorks before, so all of those issues, a lot of those issues were worked out before even fabrication started. So yeah, we definitely work together before, on all of that, fitting everything together, making sure that parts are going to fit, not getting in each other's way.
How did you improve the towing issue with the suspension adjustment?
So by moving the rack and pinion below the frame and then turning the knuckles upside down, we were able to put everything more in line. And then also by doing that and shortening the rack, we make the distance between the pivot point on those tie rods and the pivot points on the A-arms the same. So when it's a 4-bar linkage like that and it moves up and down, it has the same radius, which doesn't pull that steering tab in and out like it did before, and so that's how we fix that problem.
Okay, any other questions for this group? Let's give them a round of applause. And you will have the tractor or the what's completed so far on the tractor on display at the lab this afternoon. That's right. Okay. If you could fill out your evaluations while I find the next team. Now, we're
gonna have one person every.
so.
Somebody's gotta be Do what? Oh, yeah.
Okay, we're going to shift gears now and switch to a little more environmentally natural resource oriented project after a couple of mechanical projects. And this group they call the Landfill Ladies. And so I'll let them tell you about their project at the Enid landfill. Excuse me.
Thank you. Good afternoon, everyone, and thank you for joining us. We are Sustainable Solutions, and we're so excited that you're here for our final senior design presentation. I would ask that you hold all your questions till the end. We'll get all of them answered. I'm Katie Schlotthauer.
I'm Christian Lake. I'm Amicus Kelly.
And I'm Hannah Blankenship. And our mission statement is designing green solutions for soil and water-related problems. In August 2016, the City of Enid and the Oklahoma Department of Environmental Quality approached us with an erosion problem on the north-facing slope of the Enid landfill. This problem included rill formation, severe erosion, and sparse vegetation. And in other cases, no vegetation after a regrading effort over winter break. The top priority was the risk of trash exposure. If you get too much sediment moving away, we'll have trash exposed, and that's really something we want to avoid. And also an overall poor soil quality. So we were tasked with researching applicable erosion control strategies for landfills across the state of Oklahoma, and also developing a site-specific recommendation for that problem slope. Our customers required that we design a solution that covered the slope with vegetation to reduce erosion, that we organized our research in a user-friendly format for other landfills, and also that we were sure to evaluate using on-site materials in our solution. So at the City of Enid, they have a composting program that operates on-site at the landfill. They also have a mountain of wood chips available, a stormwater pond that might be useful for irrigation in the future, and also wastewater sludge that's already transported there from the wastewater treatment plant that's just being disposed of in the landfill that could be composted into biosolids and applied as a fertilizer on the slope. So today we're going to go through our research, modeling, and solutions. During our research phase, we made a giant list of all the erosion control products we could think of. We also took soil and water samples at our site and turned them into the OSU Swaffle lab to be tested. During the modeling phase, we used Russell 2 computer simulation to look at what solutions might be useful to model in our on-site test, which we performed from March 3rd to April 14th this semester. And finally, we'll present our solutions. We have a site-specific recommendation and also an erosion control menu. So each of our erosion control solutions was tested through research, through computer modeling, and also on-site testing. So at the beginning of this project, we were looking at technical papers, we were doing web research, looking at previous studies and patents, anything we could get our hands on that might be a solution for our slope. And what we're delivering today is that site-specific recommendation. We did incorporate on-site materials for free, and also our design solution menu, which organizes strategies into categories of the severity and the type of erosion that the solution addresses, the longevity of the solution, and also the anticipated cost. So moving into our research phase, we started with our soil samples in October of last semester. Basically what we found was that all of the soil is nutrient deficient at the landfill. You can see that the cover top soil is a little bit more nutrient rich with nitrogen and phosphorus, but for the most part, we weren't really impressed with the levels we were seeing, even in the compost. We also looked more into what just basic erosion is, and we found that the basic need is to reduce stormwater runoff and increase infiltration of that rainfall into the soil so that you don't get water moving across the surface. Erosion is divided, for our purposes, into 3 categories. Splash erosion refers to the impact that rainfall has on the soil surface, dislodging soil particles and moving them away. Sheet erosion refers to when stormwater has ponded and is moving across the surface in sheets and pulling up sheets of the soil. And then in our landfill case, the most intense type of erosion we were dealing with was rill erosion. And in that instance, water has formed channels and is carving out paths down the slope. So when we were looking at what types of products address these issues, they fell neatly into 2 different categories: cover management and support practices. Cover management solutions mainly focus on increasing the nutrient quality of the soil so that natural vegetation can begin to take root and grow. While support practices are a little more intense, there's too much sediment moving on your site for vegetation to grow, and so you have to implement some kind of structure to slow the velocity of water and cause sedimentation, for those sediment particles to fall out, so that grass can begin to grow. Moving into our modeling phase, we started with Russell 2, which is a computer program produced by the USDA and NRCS that estimates soil loss. It uses the universal soil loss equation, which has many different inputs, some of which we had to put in ourselves and others which the program automatically pulled from databases. So inputs that we put in ourselves include slope characteristics like the length of the slope and the steepness, climate characteristics like typical precipitation and temperature for Enid in the spring, and also soil characteristics. And we used our soil sampling and also the web soil survey to input those. And those were made constant during every test. But what changed during each iteration was what kind of ground cover we put on the slope and also what kind of structure we implemented, including mulch berms, compost socks, and wattles, which we'll talk about later. And this is what we found. The worst thing we could do is nothing. We're losing a ton of soil per year with no cover on the ground. And the best thing we could do, as expected, is establish a good grass cover. Even with a poor grass cover established, you're losing tens of thousands less pounds of soil every year, which is important when you're trying to keep 2 feet of cover on your slope. We definitely wanted to implement solutions on site that encouraged that good grass cover, but we also wanted to test solutions that were support practices, and we saw good results with the compost socks and the wattles and mulch berms, so we made sure to implement those. And now I'm going to turn it over to Ms. Hannah to talk about our on-site testing.
Alright, so this
introduces our characteristics and some of the overall procedures for each of the plots. First of all, we decided to use 6 different plots, and this includes a control plot. So we had 5 different erosion control materials or structures. Each plot was 10 foot wide by 40 foot long, and each one was hand seeded with a seed mixture provided by Johnston Seed Company. There was about 7 different species of grass included in this mixture, and we sprinkled that over all of the plots. We also did not add any fertilizer or irrigation water. The main reason for this is because we did not have a hydroseeder machine available to us at the time. There also wasn't a good way to get the irrigation water up on the slope. And so we decided to just leave those constant and not add anything extra to the plots. Then for simplicity, we used 5-gallon buckets and a front-end loader to measure out our materials and transport them up the slope. Our testing started on March 3rd. We installed all of the plots on March 3rd and began our testing. And then after 1 week, we came back and took our first data points. Then after week 3, we took our second data points. And after week 6, we took our third data points. And after that 6-week mark, we cleaned up our materials and concluded our testing phase. And we wanted to evaluate the success of our plots in 2 different ways. The first one here is the erosion evaluation. We did this by staking erosion pins in the ground flush with the surface. And this would allow us to estimate soil loss over the entire plot. So we could use a ruler and actually just measure from the top of the erosion pin down to see how much soil was lost over the course of the entire testing period. And this would allow us to average those results to get an understanding of the severity of sheet erosion. We also looked at the cumulative results over the entire duration of our testing. We also wanted to look at success through vegetative cover. And this was done by estimating the total canopy cover on the plots themselves. We divided the plots into 2 different sections, top and bottom, and then we took photographs of those sections. We imported that into Adobe Photoshop, and that allowed us to extract the total number of green pixels in the image, as well as the total number of pixels overall. And we only included what was in the plot boundaries itself. We added those respective numbers to each other for each image, and that allowed us to divide the total number of green pixels by the total number of pixels in the image, and give us a percentage of green in the image. And that allowed us to estimate the total amount of vegetative cover over the entire plot. And this moves into our procedures phase for all of our plots. The first one here is our compost blanket. This one was hand seeded first, and then we applied a 1.5-inch layer of the on-site compost evenly over the entire plot so that no bare surfaces could be seen. Then we installed erosion netting over the entire plot in excess of 5 feet below and 5 feet above the plot to help control any sheet erosion or movement of that compost off the plot. And then we secured the netting with 4-inch garden staples. This is our control plot, and as you can see, there's nothing on it. So we hand seeded this one, and then we left it bare, but we did add the erosion pins so that we could use this plot to compare with our other plots. You can see from this image just how rough the soil is and kind of what we were dealing with. Then this one is our manufactured compost socks. We were able to acquire materials from Minnick Materials in Oklahoma City. They gave us some compost blanket or compost sock netting with an 8-inch diameter, and it was pre-filled with compost that they provided. And each of these were in 10-foot lengths, and we decided to use 4 of them from the recommendations from the Russell modeling that we did earlier in the semester. So we placed the first compost sock at the very top of the plot, and then each of the others were placed at 10-foot intervals down from there. Then we staked them with 2-foot garden stakes at either end to secure them in place. This is the homemade compost stocks, and these are very similar to the manufactured ones. We acquired the same material, and this time we actually stuffed them ourselves with the on-site compost. And so that's the difference between those two plots. Then we followed the same procedures, placing them at 10-foot intervals with the first one at the top, and we staked them in the same manner. The fifth one is our wattles plot. And wattles are long tubular formations that are filled, they're a netting that is filled with either mulch, or sometimes you might see them with straw in them. We decided to use the on-site wood chips, and we acquired our netting material from ASP Enterprises in Wichita, Kansas. The only issue with this plot, as you might be able to see from this image, we only have 2 wattles. And the reason for this is when we went out to do our original staking of the plots, we were going to do 40 square feet of plots. Instead, once we got there and saw how much space we had and how fairly even the surface was, we decided to go ahead and do 400 square feet. And we didn't have enough time to get more netting, and so we kind of worked with what we had. We had 2 10-foot long sections of this netting, and then we hand stuffed them with the on-site wood chips to fit a 6-inch diameter. Then we placed them about 13 feet and 26 feet down from the top, and they were staked on either side at an angle to secure them in place. And the reason they weren't staked in the center like normally is because we couldn't actually get the stakes through the center because of the large wood chips. Then finally, this is our biosolids and wood chip plot. This one was kind of fun. We actually drove down to Midwest City and acquired some Class A composted biosolids. Part of the reason that we did this is we were wanting to use on-site materials, but we didn't have enough time to adjust our design to fit compliance. Class B biosolids, you have some detectable levels of pathogens, and we didn't want to have to deal with that during our implementation, so we decided to use the Class A composted biosolids. Midwest City has a commercial composting facility on site, their wastewater treatment plant. So that's why we drove down there. And this is completely safe to handle, and we didn't have to worry about any restrictions. So this one we mixed with on-site wood chips, and the reason we did this is we found a study last semester that recommended putting biosolids in combination with mulch. And this actually helps prolong the nutrient release of nitrogen, and so we decided to mimic that procedure. We also we laid out the seed first, and then we raked the biosolids and wood chip mixture over the plot and kind of incorporated it all together. Netting was also staked over this entire plot, similar to the compost blanket, and it was staked with the 4-inch garden stakes around the entire edge. Then we went ahead and built a mulch berm, as you can kind of see in the bottom of this image, and this was just to help with any of the sediment that came off of the plot or any of the leaching nutrients that may come off. We didn't want it to be getting into the stormwater pond or leaking out anywhere else. So this is some of the calculations that we did to kind of decide how much biosolids and how much wood chips we wanted. We wanted to follow a recommendation to apply biosolids at a rate similar to a nitrogen fertilizer. So we were given a recommendation to apply from Johnson Seed Company to apply fertilizer about 75 pounds of nitrogen per acre. And we found that the Midwest City compost, biosolids compost, had 34 pounds of nitrogen per dry ton of biosolids. And so we converted that to how much we needed for each plot, or for our one plot. And this came up to 60 pounds total. And we assumed about a 36% mineralization rate. And that means that the nitrogen would kind of break down. It's usable for the plants, but it would probably wash away before the grass seed could actually get established. And so we wanted to add a little bit more so that they would have enough nitrogen to actually get established. Then we used 107 pounds of wood chips, And this was according to that recommendation of the study that I mentioned earlier. We also added about 25 gallons of soil, and this was just to kind of give some substance to the mixture, as well as allow something for the biosolids to cling to and not be washed away.
So a key part of our project was to keep costs as low as possible. Initially, when we first started the project, we expected to spend about $2,400 throughout the course of the project. However, we only ended up spending about $840. This is largely due to the fact that we received a large amount of donations from both in forms of supplies and materials. And another key thing to consider is that if the city of Enid or any other landfill in the state of Oklahoma was going to implement one of these design solutions, they would not be spending such a large amount of money on travel-related expenses. So we visited the plots at weeks 1, 3, and 6, and during each of these visits, we measured the amount of soil loss, and we also took photos to document the amount of vegetative cover that had been established. So what did we discover? Our compost blanket was actually our best performer. It had the highest amount of vegetative cover. There was a low degree of sediment loss. There was some minor erosion at the base and at the top of the plot. However, it was very minor. So it was very important to this study to have a control for two main reasons. The first reason that we decided to have a control is so that we could see what would happen to the landfill if we did nothing. And also another reason that we decided to have a control group was to see, to have a basis for comparing the sediment loss data and the vegetative cover establishment. So as expected, this plot did not have a very high degree of vegetative cover established on the plot, and also there was an even distribution of soil loss throughout the face of the plot, and there was a single rill that started to form at the base of the plot. On our third plot, we decided to implement manufactured compost socks. We actually had some pretty interesting results with these. As the sediment washed down the face of the slope, the compost socks trapped the sediment, and this created a nice terracing effect. However, one negative consequence of this particular design is that we left some gaps in between the compost socks, and as a result, this created some rills on either side of the compost socks. It's important to note that if the city of Enid or any other landfill was going to implement compost socks, that these rills would not be formed because the compost socks would be installed parallel to the base of the slope. On our fourth plot, we implemented homemade compost socks. The main difference between the homemade compost socks and the manufactured compost socks is that the homemade compost socks were filled with on-site compost rather than compost from mimic materials. We had similar results. Again, we got this nice terracing effect. However, there was one main difference between the homemade compost socks and the manufactured compost socks. As you can see on the second compost sock, there was starting to be some undercutting, and we think this may be due to a variety of reasons. Possibly the soil was not compacted enough underneath the sock when it was first installed, or possibly due to the nature of the homemade compost socks. They're not as firmly compacted, they're a little bit looser than the manufactured compost socks, so they're not as strong as the manufactured ones. On our fifth plot, we implemented the homemade wattles. The grass growth was a little bit taller than the control, however, it still was not very great as we had hoped. Again, we got this nice terracing effect, however, it was not as pronounced as with the compost socks. We think this may be due to the fact the wattles are more porous than the compost socks, so as the sediment ran down the face of the slope, it did not capture the sediment as well, however, it just ran like straight through. And on our sixth and final plot, we implemented a combination of biosolids with a mulch berm constructed at the base. And this was actually our second best performing plot. It had the second highest amount of vegetative cover and a fairly low degree of sediment loss. What we have here is a closer look at the mulch berm. You can see that it did a really great job of capturing the sediment, and it might be a good solution in the future to help capture sediment as it runs down the face of the slope. So we went back to the plots at weeks 1, 3, and 6 to measure the sediment loss, And at the end of the 6 weeks, we added up the total amount of sediment loss to determine how much soil had been lost from each plot throughout the duration of the experiment. And what we discovered is that the compost blanket and the biosolids plots had the lowest amount of sediment loss. We think this may be due to a variety of reasons, mainly due to the fact that both of these plots had erosion control netting applied to the face of the slope. We think that this did a great job of keeping the soil on the slope. And another reason that there was a lower degree of sediment loss for these two plots, possibly due to the fact that they both had nutrients added, and this helps establish a vegetative cover, which also helps keep the soil on the face of the plot. So when we were looking into the literature, there were a couple of different ways to quantify vegetative cover, one of which involved uprooting the vegetation and weighing it after growing the grass, and unfortunately, we did not want to go this route because we did not want to tear up the grass that we had worked so hard to grow. And so we decided to go a different route to quantify the vegetative cover. What we did was we counted the total number of green pixels and divided that by the total number of pixels in each photograph, and we used this to determine the amount of canopy cover. And what we discovered is that the compost blanket and the biosolids plots had the highest amount of vegetative cover. And this further confirmed our observations that these two had the most grass. And we think that this may be due to the fact that both of these plots had nutrients added. So what type of obstacles did we encounter along the way? Initially, when we first started the project, we had a couple of issues with communication and chain of command. Basically, it just took us a while to figure out exactly who we needed to talk to in order to accomplish what we wanted to accomplish. Another great lesson that we learned during this project was how to deal with compliance issues and environmental regulations, and that's definitely going to help us in our future careers. And also, weather was a key constraint in this project. Due to the variation in Oklahoma's weather, it's kind of hard to predict how much rainfall we will receive, and perhaps if we had more rainfall, we might have gotten more grass. And another constraint in our project was with distance. If we were located closer to the landfill, we definitely would have visited more often, and if we had visited more often, we would have had more data points and possibly a higher degree of accuracy with our data. And another thing to note is that due to the limited nature of our schedules, we had a bit of limitations with time. We only had about 6 weeks to implement on-site testing. So now I'm going to turn it over to Amicus to give you our recommendations.
So after analyzing our results, we decided that a combination of adding nutrients to the soil and adding a design solution that would slow water as it came down the slope would be best. And we recommend doing this by adding on-site materials. We would recommend adding the compost that's on-site for a compost blanket and using the mulch that's on-site for mulch berms to go across. We were initially worried that the on-site compost wouldn't be nutritious enough to support vegetative growth, but our tests showed that it did. So the cost analysis, we based it off of about a 2/3 area, and we did this because there is some established vegetation down on the bottom and up one side of our slope, and we believe that if we could add a design solution that encouraged vegetative cover on the 2/3 critical area, that we would encourage vegetative growth along the whole slope. We did not include labor costs in our cost analysis, but we will be comparing them to the do nothing option, which is a reoccurring monthly fine of $500 to $1,000 if an erosion problem persists. So this is just a picture of our on-site critical area. You can see the area that would be considered our critical area and some of the vegetative growth that is established along the bottom and up the side. This is just a diagram to help better picture where we're hoping to place the mulch berms. We'd recommend that they get placed at 100 and 200 feet from the top of the slope. And then later, if the water velocity seems to be still too strong, placing them at 50 and 150 feet. And as you can see, the mulch berms kind of angle up on both sides, and that is our way of helping to avoid the rail formations on the sides as the water tries to take its path of least resistance down the hill. So I'm going to break the cost analysis up into 3 separate sections. The seed section, we got these numbers from Johnson Seed Company, and they break their rates down into a landscape rate and a critical rate. The landscape rate is for areas that have some established vegetation, so we would fall under the critical rate. For the nutrient blanket, we included cost options for a low, medium, and a high. We obviously recommend the low option. It does get to utilize on-site resources, but we included the medium and high options because we do believe that a higher nutrient quality could help quicken your results. Plus, we also know that Enid has a really great composting program that allows members of its community to use the compost, and we would no longer recommend using this option if it were to be an end to that program. For the support practice, we included cost analysis for the homemade mulch berms and the manufactured wattles. We did include the wattle option in case the homemade mulch berms would not want to be made, but due to the price difference and on-site resources, we definitely recommend using the homemade mulch berms. So we wanted to be able to provide erosion control options for areas and landfills in Oklahoma that we didn't get to know as well as our Enid site. And we decided to do this by creating our erosion control menu. And it works like a flow chart that goes through the different types and severity of erosion, different cost options, longevity, and things like that. The menu also has little descriptions, short descriptions of the design solutions to help you best decide what would be perfect for your erosion control issues. So the first section of the menu is under low severity. This is often due to splash erosion, and you can kind of notice splash erosion by crust forming on the surface. To fix this, you need to add nutrients so that there can be some vegetative growth that can ultimately help reduce rainfall impact. The second section, the average severity section, this is usually due to sheet erosion, and this usually has some small amounts of vegetative cover, but it also has roots starting to show as they're being uprooted. And this needs a little bit more of a severe approach. It's going to need nutrients to help encourage vegetative cover, but it's also going to need a support practice added that will either slow the water velocity or channel it in a different way altogether. And for extreme severity, this is often real erosion where there is no vegetative cover and the water has started to channel into the soil and the slope. This needs added nutrients to help vegetative growth. It needs the rills that are previous to be filled in, and it needs support practices to help slow the water velocity. So we like that the erosion control menu can be used to help identify a problem and decide what solution will be the best, but we also hope that it gets used in a proactive manner where if there's reoccurring issues or when new cells are being built at landfills, that these design solutions can be implemented to stop erosion before it even starts, ultimately saving time and money. In the future, we hope that Enid can continue to watch our plots. We did leave our design solutions up on site so that they could be watched into the future since we had to cut our testing short. We do think that some of the information that we've collected could be used for further planning, like knowing that the topsoil is slightly more nutritious. If it could be held back and only used on the exterior slopes and not as daily cover, that could be helpful. And then also as new cells are being built, if compost can be incorporated so that possibly we would avoid adding a compost blanket in the future. We also think it would be a great opportunity for Enid in the future to look into stabilizing the biosolids that come through their facility. This would help provide another great source of nutrients and reduce the amount of biosolids that are lost as waste. And finally, we hope that the menu is continually updated with trending solutions so that the best available options are always available. We wanted to thank everyone who's answered our questions or donated time or resources or funds for us and anyone who's helped guide us along the way. Thank you for coming to our presentation. Does anyone have any questions?
Thank you.
I had one question. When you said that you got the seed from the Johnson Seed Company, were these native Oklahoma grasses or were these a mixture of others, or do you know?
It was a mix of, I think, about 7 different seed varieties. In the report, there are USDA plant fact sheets that tell you more about the different varieties, and we also have the mix from Johnston if you'd like to look at it.
Okay.
I have a question. So it seemed like the burns basically performed lower or at the control plot. Why is that? What do you think?
The compost socks?
Yeah, and the waddles,
So,
both, yeah,
Right.
for the soil lots and vegetable cover.
yeah, that was very frustrating for us. First, I would like to clarify that quantifying our sediment loss was more difficult than we anticipated. We expected to measure the amount of soil that was lost over time. And when we came back, some of our stakes were covered with soil, and we didn't think about how we could measure that sediment shifting. And we didn't want to dig down
Right.
and cause more erosion by finding them. And so our numbers are a little skewed. Also, I'm not sure we have a good picture here, but I can show you at the demo. The soil surfaces above the plots were not equal. And so we could have had more sediment moving over those particular plots.
There were some like rills already starting to form from where our front end loader had been, and we think some of the soil above the plots that got like higher velocity channeling definitely affected how much soil loss we saw in the plots.
Did your team take any weather element observations, amounts of rainfall, wind direction, dew points, those kind of things?
I did pull the rainfall data from the Mesonet at the last, on the last day of our testing. But basically you can see here that we got way more rain in between week 3 and week 6. We didn't really see any sediment moving until then. And that's all we tabulated into our experiment.
Have you either seen or heard any reports about what it looks like after last weekend?
I have another question. So you mentioned you put the netting over both the biosolids and the compost, and that provided some structural stability. In a real world situation, that's pretty unrealistic. Do you have recommendations or ideas about alternatives to that?
We didn't end up recommending adding that because we knew it wouldn't be very feasible. We wanted to do it for the plot just for keeping our plots like very singular to their own side. We didn't want things blowing around. But the things that we read said that if we'd gone above 2 or 3 inches of adding compost or things like that, that we would need to have netting over it, but that if we recommended something smaller, that it would be okay to not have the netting on the full slope. So that's why we were able to suggest
And
that.
on that point, how did you choose 1.5 inches for compost?
There are EPA fact sheets for applying compost blankets, and they have different recommendations based on your soil type and stuff like other factors like that.
I got a question. So what type of nitrogen is it, and does it have a leachate?
Collection system.
No, what type of nitrogen is it? Is it
It's
like a
just-
dumped nitrogen? And does it have any leachate coming out?
Yes, yeah, they do collect leachate.
If you look into using the leachate to grow or ecologically grow those values.
Yeah, we did briefly look into the leachate in last semester as we were doing our literature study and such. And we decided, especially with the option of using the biosolids, we felt like that was a more, I guess, reputable option. The leachate a lot of times has a high salinity or other contaminants in it that make it difficult to actually put on a slope. If you're irrigating with it, then you have to recollect it somewhere else. And so we didn't want it getting into the groundwater or other surface water ponds if it didn't meet regulations.
Once this vegetation is established, did you all look into what type of long-term operation and maintenance costs or reoccurring operations and maintenance to maintain that grass once it became established, mowing or?
We didn't look into like what it would cost to mow the slope. I know that the seed mix that we planted is successful in Chickasha and El Reno, and so we might go to them and ask if they were curious. But really, the maintenance that we looked into would be maintenance like on our compost blanket and on the mulcher. So they might have to be checked after like a big rain event or maybe once a year. building places.
Any other questions for this group? Okay, let's give them a round of applause. And you will have some interesting things on display at the BAE lab, and I'm pretty sure it's not trash from the landfill. Maybe a little trash. So I encourage you afterwards to go look at their display. So thank you. Well.
Quick rotation. Because of well, no, they're probably about yeah, I think so. Yeah, that's right. I don't know if he's just with this or if he's doing we brought it on
Yeah, GoPro is good. We're taking the video.
You're a TV, you're a
That's helpful. That is nice to have a community.
We, long time back. Okay, we're moving right along. We're going to look at something a little bit different. This next project is with US Roasters Corporation in Oklahoma City. We've done projects with them in the past on coffee roasting, but this is a little different. We're looking at processing cocoa beans. So with that, I'll turn it over to the cocoa bean team.
Hello, ladies and gentlemen. My name is Montana Wells.
I'm Joseph Barnes.
And my name is Benjamin Jenkins. And we are Triad Enterprises. Triad Enterprises is a small local firm supplying various services, including but not limited to engineering consultation and small-scale manufacturing. Our mission statement is partnering with others to help them reach their goal. Our client is US Roaster Corp. US Roaster Corp is located in Oklahoma City, Oklahoma, and was founded by Dan Jolliffe. He has served the coffee roasting industry for over 33 years, and he specializes in new roaster fabrication and rebuilding older roasters, as well as coffee grinders. He provides a wide range of coffee roasters, anywhere from 3 ounces to 300 kilograms. Here's a few examples of his award-winning coffee roasters. So our problem statement was to design, build, and test a cocoa bean winnower that meets some specifications. It needs to be affordable for bean-to-bar chocolate producers. It needs to be able to be fabricated at US Roaster Corp facilities. And then it also needs to incorporate competitive features such as unsupervised operation, be easily adjustable, and be quiet and fast. So here's a cross-section of a cocoa nib. In the middle, you'll see the cocoa nib, and it has quite a few fracture marks. This is due to the roasting process, and it becomes quite brittle. And whenever you apply any sort of pressure, it sort of crumbles along those fracture lines. Along the outside is the cocoa hull, and it's the part that needs to be removed. It's thin, brittle, kind of papery, and it needs to be removed because it'll make chocolate rather bitter, and it can also contain mycotoxins, heavy metals, and pesticides. So a winnower is an apparatus that separates the desired portion of a material from the undesired portion. So for our project, we'll start with whole roasted cocoa beans, and then we crush them, and that separates the outer, the chaff part from the nib, and then we separate the hulls from the nibs. So we set a few specifications and goals that we wanted to meet with our project. And so we wanted it to be able to winnow at a rate of 100 pounds per hour. We needed it to operate at an efficiency of greater than 95%. And this means that there's no more than 5% of the nibs in the waste stream. We needed to not allow greater than 2% chaff in the final nib output. That's an industry standard. So greater than 2%, and it will affect the taste of the chocolate bar or whatever chocolate product you're making. The retail price we were shooting for was between $4,000 and $6,000, so we wanted to build it for less than that for a profit margin. And then we wanted to also minimize the moving parts and make it easily cleaned, which are key points for food service products. So the general flow of our project that we followed, we first researched the physical properties of cocoa beans. We felt that if we really understood how cocoa beans worked and what they were made of, then it would help us throughout our project to model more efficiently, so we didn't have to spend so much time in the iteration phase. So then from there we moved on to the cracking method. We designed the cracking method based on the physical properties, and we went through several iterations to try to find the best way. From there we moved on to sorting, and then finally separating the nibs and the chaff. Here's a few winnowers in industry. We started off our project doing quite a bit of research with what's already out there. So on the left, you'll see the Bear winnower type BWI, and it's an industrial size winnower. It can winnow at a rate of 1,100 to 6,600 pounds per hour, which is a lot of beans. The nib content in the chaff is 0.25%, and then the chaff content in the nibs is 1.75. More on our side of things is the right side, the right winnower. It's the Vortex winnower by Brooklyn Cocoa. It winnows at a rate of 88 pounds per hour, and the nib content in the chaff is 0.25, and the chaff content in the nibs is 0.2, and those numbers both come from running the beans through twice. And it retails at a price of $34,000, which puts it out of the reach of many startup chocolatiers. Last fall, we had the opportunity to lead 2 freshman groups. We were tasked with giving them a project that sort of helped them understand the engineering design process. So our first group, we gave them the job to determine a viable air velocity range to separate the chaff from the nib. They utilized the air velocity separator in the Biosystems lab to determine this range. They used the terminal velocity of the chaff to lift it away from the nibs, but still keep the nibs down below. They determined an air velocity of 5.15 meters per second, gave the best sort, but a range of 5 to 6 meters per second was viable. Our second freshman group was tasked with designing a hopper that meets some specifications that we gave them. We told them it must hold 100 pounds of cocoa beans, they must determine an appropriate food grade material, and it must not exceed a loading height of 5 feet. Along with that, they had to make a model in CAD software of their choice of their hopper, and then they also had to contact a material supplier and estimate a price. So last October, we got to visit Izzard Chocolate, which is a chocolatier in Little Rock, Arkansas. They were founded in 2014, and their owner introduced us to the chocolate process as a whole, and he sort of talked to us about his winnower and some of the issues that he had with it and some things that he would like to see better. So here we have a video of his current winnower. He made it himself, and so he uses a food processor to grind the cocoa beans, and this sort of crushes them too far, he makes a lot of dust. He estimates that he loses about 25% of the viable nibs. And when cocoa beans are about $700 for 100 pounds, that's a lot of money if you're losing a quarter of it. So he would like to see a better solution where he has less dust and can keep more of his nibs. He would also like it to be more aesthetically pleasing and to be faster. He said it takes him all day to winnow just one batch of cocoa beans, and then having to do that twice a week really takes up time on a process that shouldn't take that long. Last fall we did some testing. Some of the physical properties that we tested, we got some roasted cocoa beans from our client, and we measured 122 of them. We found that the average weight was 1.19 grams, the max being 2 grams and the minimum being 0.5 grams. The average sphericity, which is how close the cocoa bean resembles a perfect sphere, is 0.61, so it's average. And then a max diameter of 28.97 millimeters, and then a minimum diameter of 5.01. And that really shows the variability and physical properties of biological materials. It's very hard to design a system that can handle all of these types of beans. And we have a short video of some more testing we did. We used liquid nitrogen to freeze the beans. So we froze the beans, and then we loaded them into in between the wood blocks, and then we pulled the metal plate, and we were hoping that the liquid nitrogen would freeze the outside, the hull, so whenever the impact would hit it, it would just kind of shatter. Unfortunately, we didn't get those results, and we determined that it wasn't a route that we should take.
So at the end of last semester, we came up with a couple options for cracking the beans. The cracking is a pretty important part because however the beans look after they're cracked sort of determines how you go about separating them. And so one of our designs that we had is this design you see here. It's our high-risk design, and it's an impact design. So we noticed that the beans actually cracked themselves really well and stayed in fairly large pieces when impacted or dropped. And so we came up with this design, which has a paddle wheel that would spin and impact the wheels, impact the beans to sort of crack and keep them in larger pieces. This design would have been really simple to manufacture and build, but there's a lot of dynamic elements involved that we would have to test to ensure that the beans would get cracked consistently across all of their different varieties. And so we came up with another option, which is much more common. It's a roller design. It's almost an industry standard. It's really robust. The output of the beans is very consistent. It's well known. And given our time constraints and the amount of testing that would be required for our impact design, we opted to go with a roller design. And so moving on, once we decided we were going to go with roller, we found this roller mill in our department's annex, cleaned it all off, and installed a variable drive on it. And we were able to use this machine to test various roller gaps, various roller speeds, and multiple passes on the beans to simulate if there was a stacked roller design. Yeah, there's a video watching it sort of give you an idea of how it works. You can see the rollers there, and that's down in the hopper. It's really ate some beans. So after we would roll the beans, we would want to get some numbers on how well the beans were cracked. So we utilized a machine called a rototap, and essentially you stack the sieves up, and it helps separate the beans based on their particle size. And so we came up with a range of sieves that were useful for us, and after every roll test we did, we would rototap the beans and evaluate how well the crack came out. Here's a short video demonstrating how the rototap operates. So it's pretty coarse, but it makes pretty simple sense there. And it just beats it until they fall through. So here's some of our data. These graphs here are comparing both a 7mm roller gap and a 9mm roller gap. And within each graph, you have a high speed and a low speed roller process. As you can see in the 9mm roller gap on the right, you have very little dust, and the dust is what we would consider waste because you can't sort it. However, you see a whole lot of material that got caught in the first sieve. And that's because there were whole beans that didn't get crushed, and so if you have a whole bean, you can't really separate it. But you can also notice in 7mm you have a much nicer spread of material throughout all the sieve stages, but you also do have much more dust. Also notice that the slower speeds, the orange columns, did mitigate some of the dust production in the 7mm roller distance. This graph shows various roller gaps at a single speed. So here we have a 7mm, an 8mm, and a 9mm roller gap. Again, we can see that the 9mm roller gap had very little dust waste, but again, we have a large amount of large particles at the very first sieve, which was due to beans not being cracked. You can see that 8mm was our threshold that we found for getting all the beans to be fully cracked and to start seeing a more uniform spread across all of our sieve sizes. And then 7mm also helped mitigate some of the dust and waste production. Further testing, we tested a double pass. So on the graph to our left, we have a double pass at 12mm and then the second pass at 10mm. And we compared that with a 10mm and an 8mm double pass. And the idea of doing the double pass at such wide gaps was that the beans may have been compromised on the first pass, and through the second pass they would have actually been cracked and would have been able to winnow. And also 2 passes we were hoping to mitigate some of the dust waste production. Again, we can see at the 12 and 10mm double pass that there was still a fairly considerable amount of beans that had been uncrushed in our top sieve, again explaining the low dust or waste production. But we can also see that the 10 and 8mm had a fairly good spread and was more successful than the larger gaps. When we compared a double roller of a 10mm and then passing an 8mm with a single pass at an 8mm roller gap, we see that we mitigated some of the dust production against a single roller, but we decided that given our time constraints and our budget, we would go ahead and pursue a single roller design. But we did see evidence that multiple rollers does help mitigate the dust or waste production. Here we have a model of our prototype. It is a fairly robust design. It's got rollers. It's got an easily removable hopper. It's got a fairly small shop floor plan, floor space. It's fairly easy to operate. There's 2 switches, and then the operator just puts in the beans, and it can process beans at a very high capacity. What makes this model up is starting with our rollers and our housing. So we have a 1/2-inch steel plate housing, which houses 2 12-inch long by 7-inch diameter rollers that have been grooved to help feed the beans in. Those are supported by food grade pillow blocks, bearings with 1-inch shafts, powered by Schedule 40 chain, and we featured a pivot roller in there to adjust the gap using linkages and a threaded nut so that within our range you can infinitely adjust the gap. Moving on beyond that, to drive our rollers, so to spec out our motor, we took our roller mill that we had access to test with, and we loaded up the rollers full of beans as worst case scenario, and then pulled up on it to see how much torque was going to be required to power through fully clogged rollers. We then decided how much torque that required per inch of roller, scaled it up to our 12-inch rollers, and we came up with a number of around or greater than 600 inch-pounds of torque would be required. Taking that to the marketplace, we were able to find this Dayton gear motor, and this gear motor is a 1 horsepower motor with 605 inch-pounds of torque at 85 RPM, and it was going to be well up to the task. We double-checked to make sure that that motor would be well enough. Used our horsepower equation, and the horsepower equation said that it needed to spin at 105 RPM, and this was going to be spinning less than that, so it was going to be perfect for our application. To power this motor, because it's a 3-phase 220-volt motor, we had to use a variable frequency drive, and we went with an ABB ACS 310 variable frequency drive. It features the ability to input a single phase 220 volt and output 3-phase 220 volt to the motor to make it more accessible to more wall outlets. It features a ton of built-in programmable options as far as startup rate, starting torque, dwell times, and things like that. More features than we've had time to test with, but it's a very capable and good product for what we're trying to get done. Moving on, we had initially planned on having a drum, which is a rotating drum, and we would have 3 different stages of sieve sizes spec'd out here, which would help separate the beans. And by sorting the beans to their various particle sizes, we would be able to fine-tune the velocity that would be required to separate the nibs from the chaff. But given our time constraints and how simple the design would be, we just sort of left that out and moved on. That would have been housed in the frame that we actually did build for our prototype, which is a very simple design, 1¼ by 1¼ square tubing throughout. It would be a simple fabrication, quick and easy, very good for low-cost production. Moving on to the separation, we utilized a shop vac with 170 cubic feet per minute of airflow. What else do we have? We have a cyclone separator to help separate the dust out to keep it from clogging up the vacuum. We use PVC pipes for our routing, and we have 2 discriminator valves involved to fine-tune the amount of suction force that the beans see as they're processing through to help sort the chaff from the nib and improve efficiency that bean to bar producer may see. What was required in producing this prototype was obviously assembly, but there was a lot of lessons learned in how you tolerance and call out threads and things like that. So we ran into some issues, but it's important to test fit everything. So all the way to the right we see a test mock-up with the roller body just tacked together. So we went ahead and mocked everything up before we had everything fully welded. Here we have the PVC getting test fit before it was glued. So it's important to go through and make sure that everything will match up before you set everything up irreversibly. So here we have the test fit of our roller and roller bodies with our bearings. And here we found a lot of issues that we needed to address before moving on with fitment, tolerancing, and things like that. One of the things you could note here is that the shaft on the motor goes out to the wrong side. We knew that going into it, but when we reviewed the parts diagrams of the motor, we found that it is offered that you could swap the shaft. And so we went ahead and purchased that, and having to swap the shaft was part of the assembly process for us. And then here we have our finalized prototype with all of the pieces put together.
So we also did some finalized testing on our prototype, and we start off with the actual cracking portion, of course. So with the cracking portion, after testing the rollers in the VFD, we found that the best frequency to actually crack the beans was at 30 hertz. And basically what this means is that 30 hertz is the frequency that the rollers will, the input frequency, excuse me. At this frequency, we found that we had consistent cracking all throughout, and the beans were continually just being able to go through and be fed through. We did notice, however, that at lower frequencies, we had a jamming issue within our rollers. The beans would actually clog up the rollers and prevent them from actually going through and feeding through like that. If overloaded, again, the rollers were just jammed. Another issue that we found was that the spring tension on the adjustment feature was insufficient to keep the rollers in place. The actual force that the beans being cracked and pushed through was pushing the 2 rollers apart. And that was making a negative impact on the consistency of our cracking, because some beans were able to get through if they were pushed through, if the rollers were not actually jammed. With the winnower, we were able to find that the air velocity going through it was capable of pulling out almost all the beans, even whole beans. So we knew that even if any crushed bean that we actually it would be within our range to actually winnow out. But we did notice that large volumes of cocoa beans greatly reduced the amount of efficiency that we had with winnowing. Basically, our system just got overloaded with too much in the air, and there wasn't enough air pulling up through it to actually winnow it properly. And we would get too much chaff within our nibs, and it wasn't at all what sort. We do believe though that the trommel sorting process would greatly help this issue, because not only would it separate the nibs and chaff into precise ranges of particle sizes, which then can be used to adjust the separation proportion to specific particle sizes, but also alleviates the total amount of volume that one individual sorter, air separator, has to deal with. We did also notice that we had to actually manually feed the winnower to keep it at the rate that was required, because just dumping in, we weren't able to do it at a slow enough speed for it to feed properly. And so we would actually just have to manually dump in the beans. This kind of negated our goal of actually being able to just leave it there alone and have it run, like turn it on, walk away, you're fine. Currently, with the prototype as is, you have to manually do it, which is something that we would like to address. We have a video right here of me. So as you can see right now, I am tapping in the beans through our winnower, and I'm trying to keep it at a constant rate just to basically make sure it doesn't jam. And we basically went here, we did this over a period of a minute, we're trying to get close, because the amount of cocoa beans we had in there would be close to 1.6 pounds, which 100 pounds of cocoa beans divided by 60, that's 1.6 pounds a minute, which is why we were kind of going for that sample size. At this actual sample size, we were able to figure out that should the feed rate be kept constant around this rate, we were able to get actual efficiencies that we were looking for as far as the winnowing and actually as far as waste and nib loss. So testing results of actually, once we were able to not only calibrate the sorting component of our winnower and do the manual feed rate in, we were able to actually reach the feed rate of 1.6 pounds per minute, which will be scaled up to 100 pounds per hour, which we were really happy about. We found the winnowing efficiency, a lot of times we got up to 98%. So right here, as far as you can see, the waste portion, we have the nib portion right here. This is this is what we want to keep. This is what you're going to make the chocolate out of. And this waste portion is basically throwaway. It's the chaff, it's the very fine dust particles that you can't salvage within the nibs. And from this, we were able to find very little actual salvageable or usable nibs. So that was a very good indication. And this chaff right here, this chaff was actually picked out of the total nibs, as you can see right there, our product stream, indicating that while there was still chaff within it, there was still a very small proportion. And from a lot of the samples we were getting around 1 to 1.7% chaff within the winnowed cocoa, which is very good. It's still below the 2% range. And actually, if we can adjust the feed rate issue, would be very competitive. Moving on to the financial breakdown of the winnower, our overall budget for this prototype was $3,000. And once all said and done, the material cost of the project ended up being almost $2,000. With the cost of control systems, the VFD, being around $300. We did not include labor costs, simply because through the labor donations of Mr. Ball, and also utilizing the Biosystems machinery lab and the technicians there, they all were able to help us fabricate the entire process, and so that kind of no charge to us, which we were very fortunate of. Another thing that we were able to do, we got a direct donation from the Delaware Manufacturing. They actually donated the cylinders, the steel cylinders that we used to make our rollers. And that was valued at $348. And so that was actually a big help on us, and that did not go to our cost for the prototype. So at the end of the day, our prototype cost ended up being around $2,000, which was well below our budget range. The final design, financial breakdown. Our target production cost was from $3,000 to $4,000, so that way we can hopefully turn a profit after like selling at like probably $6,000 or $4,000. After you take into the cost of the cracker, the trommel separation mechanism, and also the trommel sorting, and then the separation part, the material cost for the actual product would be about $3,500, which was significantly more than what our prototype cost was going to be. The control costs, what we would estimate would be $576, and then labor was calculated. We basically took the pretty well the average fabrication technician hourly wage of $20, multiply that by 3 for 3 workers working, and then an 80 hours for 2 40-hour work weeks. We believe that we kind of believe like this would be a very good conservative estimate to figure out how much labor would actually be able to put into that. And labor, as you can see, is a significant portion of the final cost of the our final estimated cost was $8,285, which is out of our target range. And so in that aspect, we did not quite make that. Moving on to perhaps the ways of improvement, we developed this tool called the Failure Modes Effects Analysis. And of this, we basically input different things where we see failures within our prototype and within our final design. And from there, we assign values based on severity, rate of occurrence, and then the level of controls that we have in place. And we assign a value to that, and from there, we calculate what would be our main parts. As you can see, our top 3 were operator safety, roller movement during cracking, and then also food contamination or food safety. Those are the 3 areas that we really feel like we do need to address and focus in on any more iterations of this design. So with our recommendations, the first one is operation safety. Right off the bat, we need to add a chain guard. We weren't able, on the cracker assembly, it was powered by the motor, which turned the chain to turn the gears. Right now, there is not an actual guard around that, and so that is open to air, and it is possible for someone to come up and stick their hand in it and get caught and lose a finger. That is very bad, and we've actually on a prototype had to tape off the back area of the motor just to make sure that no one tries to go over there while it's in operation. So that's just the first one. Unfortunately, we weren't able to address that quick enough within this prototype. The next one is add emergency shut-off controls when areas of moving parts are accessed. So let's say the guard for the chains is taken off, or someone tries to get in or around the rollers while it's rolling. We would like to initiate an emergency shut-off where the entire system shuts down to prevent anyone from getting hurt in that aspect. On subsequent iterations, we would like to make the window shorter overall. It's a little over 5 feet right now, and so even someone my height, it would be hard for me to fully load it to capacity. So not only is that kind of dangerous, it's kind of it's not very ergonomic on any person, but also making it shorter will make the maintenance overall easier and cleaning of the product easier. And finally, we would like to reduce the entire weight of the machine. Right now, it's a very heavy machine. You cannot just lift it up and move it wherever you want. And so that really kind of makes it hard. And also add, of course, more warning labels overall throughout the design. So on the roller movement, what we're planning on doing would be what we would do was to increase the spring tension and add a spring guide to decrease or eliminate roller movement. Basically, we want to make the shoe stronger. That way, when the beans do go through the rollers, it's less likely that they'll be able to push back and not crack in that aspect. Finally, on food contamination, we would really like to upgrade all the materials to food grade materials. While that would actually increase the materials cost for design, we believe that in the long run, it would be not only a better selling point, but also would make design just overall more safe and in some cases even more efficient. And so a couple of materials that we may suggest would be, of course, stainless steel or EU, H, and V, W, excuse me. The last part is to make all components easier to disassemble. Right now, even with our prototype, all the piping for the separation component, they're all PVC, they're glued together, you can't take them apart. So that indicates that there may be many chances for particles to accumulate within the piping, and that would be very hard to get in to reach, and that's a food safety concern. And so that really needs to be addressed, and also other issues throughout the, even like with the rollers, and making sure we get in there, get them complete properly. So that really does need to be taken into consideration in further iterations. So comparing our goals and specifications. So with the winnowing rate, we were theoretically able to reach the 100 pounds per hour, but that is with manual feeding on that aspect of it. So while our winnower can reach that rate, you do have to, of course, be there all the time, which defeats the purpose of having it automatically. We were actually able to either get the efficiency of 95%, and in some cases, from our testings, we even got a little bit better on that aspect, so we were very happy on that. Typically, we got very little nib loss within our waste stream. On the 2% chaff in the product stream, some of our samples, when we calibrated really well, we got up to 1%, and then some of them, when the calibration maybe got out or perhaps our feed rate got messed up, it would be like 1.7. Regardless, we never ever got a chaff percentage by weight more than 2% throughout any of our samples that we were able to take. For the production costs of 3,000, 4,000, we were not able to meet that goal. There may be ways actually to reduce the production costs because a lot of the materials that we bought were wholesale, like we bought them straight from the store. And so there may be ways around that. And also, depending on what materials you make or decide to use in the future, could also bring that down. Easy clean, that still needs to be improved overall. There's still a few key points that would cause some food safety concerns and that need to be addressed. And finally, moving parts. Really, the only moving parts that we have on this design is the cracker. Everything else is either gravity fed or suction. And so in that aspect, we really felt like we did a good job. Overall lessons learned, we had organization, communication, prioritization. Basically, these are just general things that we felt like we learned during our design, during year design. With organization, we felt like we kind of learned how important it is to really focus and divide the workload and figure out whose role is what and how you're going to go about doing that. With communication, it is very vital that everyone on your team knows exactly what's going on, how you're going to do that, and just who you need to talk to get it done. Not only between us, faculty, even our own client, just how important communication is. And then finally, prioritization. With that one, just knowing not to get too caught up on one specific aspect of the design and letting a few perhaps fall on the wayside, just being able to have a good grasp on everything, what you need to do to get it done. So with that, do we have any questions?
Give this group a round of applause.
Between the roasting and cracking, does it matter what that length of time is or what the storage of the beans are between the end of the roasting process and the...
That would be kind of up to the actual owner of the facility. It is probably suggested that once you immediately roast it, you then crack it. So a lot of like the facility that we went to, the man who was making the chocolate, he wanted to basically roast the beans, then crack them, winnow them, sort them out, and then immediately start making chocolate, because if you do leave the bean, like even the nibs out for longer, there is a chance that they could, get contaminated.
So he was putting warm beans into his cracker?
Yeah, his beans, for the most part. He would let them cool to a certain extent, but then transfer them over to the oven.
Did you guys ever look into textured rollers, more of like a mill roller, or are all the rollers for the beans smooth?
Our rollers actually aren't smooth. They have grooves cut into them. So, yes. We did try with smooth rollers as well in the lab, and it didn't work very well. It didn't grab onto them, so we did add grooves to the rollers, and it does help grab the beans and force them through.
I'll talk about these, you can come back. But anyway, how many lines per inch were you running the rollers cut? I didn't see that when it came in the shop. How many lines per inch were you cutting across the roller?
I don't remember. It was
You do range cuts or all longitudinal cuts?
all longitudinal.
All longitudinal. Not good.
It was the largest tooth cutter you guys had.
Do you think that the depth of the cuts or the amount of cuts per inch make a difference in the product?
I think as long as there are grooves, it'll help mitigate any sliding of the beans. At some point, you're balancing. At some point, you'll start to grab the beans, and then at some point, you're going to make the rollers hold on to the cracked beans and make it a little more difficult to clean them. and have more bean buildup. So the smoothness, the teeth per inch, and the depth, you're starting to get into sanitation, cleaning, maintenance, cleaning schedules and things like that. But for the most part, as long as there's some texture, it'll grip the beans. But the fear would be having to clean them more often and how much the beans stick to the rollers themselves.
The bean sticking to the roller is a problem, the roller maybe have a wipe on it or something?
Yeah, we weren't able to incorporate a wiper. We had planned to, but that would definitely help keep the beans to sort of self-clean themselves off the rollers.
We'd like to have your comments on the size cuts you think you work good on the report. Do you think it would have been better served with a longitudinal cut and a ring together, or should you do the two longitudinal like together?
We didn't get to test with any kind of spiral cut mill rollers, so we don't really know what effects that would have. And at this point, the teeth on the rollers haven't really been the limiting factor. They grip well enough to bog down the motor, so that's not really what's limiting us at this point. We have a lot of the right elements. I think the elements we have just may not be well balanced with each other.
So I think you did a nature as well. Dig into the kind of information. I'm gonna stop and answer each other's questions and I'll come back.
Question, sir?
Is both of your rollers run at the same RPM?
Yes, sir.
Okay, in the wheat industry, to make flour, one roller runs faster than the other one. And that strips the bran off of the layer of wheat. And I was curious if you would run one roll faster than the other one, but a roll that bean.
Yeah, we were exposed to very non-matched speed rollers when we were investigating some of the coffee bean grinders that we sort of were inspired by on our roller design, but we never had the opportunity to test various speeds. We could have probably bought some different pulleys for our test roller mill, but we didn't actually test any of the various speeds, so that's a whole other avenue that may increase or decrease the dust production on the roller mill. So,
how do coffee beans differ from cocoa beans?
Coffee beans are a lot harder overall. Cocoa beans are a lot softer, so they have a lot higher fat content. So when you do crush them, we always have the issue of actually maybe getting some of that fat out and collecting on the rollers, collecting throughout the system. From as I understand it, we don't see that as much with coffee beans. But that's probably the main differences that I would suggest.
Why did you use a three-phase motor? Could you have used a single phase and then reduce the cost of your controller as well?
That was sort of driven by the torque requirements that we tested with. So we had already cut our rollers, and then when we determined how much torque it used on our test roller mill, we had to scale that up for the rollers we had made. And so had we found a single phase with that much torque, I'm sure we would have gone with it, but we weren't able to find one, so we had to go with a three-phase motor.
Any other questions?
I didn't quite, on your prototype that you built in the lab, I didn't quite pick up on what you were using for a separator there. What did you finally do on your prototype to separate?
Go back.
So we used a shop vac, and that provided our section. So the shop vac is connected to the cyclone with the reddish black hose. It's in the back. The cyclone sucks the chaff out and it spins it down into the waste bucket, the black bucket, so that it doesn't go into the vacuum and clog up the air filter. And then we used PVC. It's in front of the machine, and so the nib or the beans that are crushed fall down, and then due to the vacuum, the chaff goes up and the nibs fall down. And so we have two.
So point with your finger on your finger. I'm lost in your plumbing.
Okay, so here's the inlet to the PVC.
Okay.
I'm going to decide.
Okay, there might be a better angle.
Go to the ones. Yeah, I had that separation.
So we put the beans in the hopper, and then our roller housing is in here. So it rolls down through and gets crushed. Then we have a funnel that the crushed nibs and the hulls go through. We have a PVC tubing attached there. So then it falls down through there. And then we have it drops here, and that's where the nibs go. And then the chaff goes up. And so we have a valve here and a valve down here. And those are discriminator valves, so we can open and shut them to control the airspeed. For our final design, when we would have a trommel in this area, we would have 3 basically, so that we could separate based on the size. So the larger sizes, obviously the chaff needs a bit of a higher air velocity, and then as you go down in size, the chaff requires less. So that would just increase our efficiencies. And so the chaff gets sucked in through there, it spins around in the cyclone and falls down in there.
Okay, so here's my follow-up question.
Okay.
Your data appeared that you were doing a very good job of separation. And so why wouldn't you stick with a similar, why are you trying to improve your separation when you've already surpassed your goals for separation when a very simple device seems to be doing the job?
Mostly because it would make it more marketable. Some of the other winnowers that we found, they had very high efficiencies, well over 99%. Like 0.2. And so our client Dan, he seemed to want a very high efficiency. He thought that would be a good selling point, especially if it was at a lower price than some of the other winnowers that are over $30,000. Another suggestion that we did have that's in our report is to have various models. So maybe we could have a lower model that's a bit cheaper like this, and then have upper models maybe with dual stage rollers and a trommel or some other system.
Yes, very good, thank you.
Okay, let's give this group a round. It looks like we have a huge crowd building out in the lobby for the last presentation. This one has a little bit of local political intrigue attached to it. Good job, guys.
Oh, you're fine.
I want to grab my
Oh, it's on the back.
Yeah.
Gotta really try to be in the way.
Even if I say it, I'm not gonna say.
Yeah.
Yeah, we already got ours. We got a little
That's the laser monitor. That is the laser. Okay, well, this is our final group, and like I said, this is a little bit of a local project, and they're working with the Parkview Estates Homeowners Association, somewhat in conjunction with the City of Stillwater Engineering Department, and they are looking at water issues, which we either have not enough or too much. So with that, I'll turn it over to our last team.
All right, hello everybody. We are Cowboys Stormwater Management. My name is Zach Bradley.
I'm Riley Jones.
I'm Grant Moore.
And I'm Derek West.
And we've been tasked with dealing with the stormwater management issues at Parkview Estates. I will ask everyone to hold their questions till the very end of the presentation. So just when we got started, we wanted to come up with a mission, kind of a direction for us as a group. So our mission statement we came up with was that Cowboys Stormwater Management team was to design and implement sustainable storm and surface water systems that control erosion damage from stormwater runoff, improve urban development, and enhance quality of life in Stillwater, Oklahoma. Just a quick overview of our project. Our client was the Parkview Estates Homeowners Association. Parkview Estates itself was established in 1976. The Homeowners Association was established the next year in 1977, and they currently preside over 230 homes. Our period of performance was, obviously, we started in the fall semester. We started with 3 meetings with the Homeowners Association. What they really wanted from us was a delivery of cost-based solutions, kind of broken up for each problem area. And then during the spring, we met with them at the beginning of the semester to narrow down on the solutions, find one, and kind of move forward with that solution for each site. That being said, from those meetings, we came up with a few requirements from them. They wanted to eliminate the ponding in their streets and yards. They wanted to reduce erosion in both the public areas and along the stream banks of the stream in their green space. And then they wanted us in the fall to provide them with 3 cost-based solution options. From these requirements, we came up with a few constraints. Obviously, feasible cost-benefit ratio is a big one. You want to get as much bang for your buck out of your design. Of course, safe was huge. They wanted it to be naturally aesthetic and have a long lifespan. And then with that, they also wanted us to be able to come back in and potentially be able to add stuff in the future. They wanted to be able to kind of tack on to this current design later on where some more money might be available. And then of course, budget is always a big constraint.
So just a little quick project review. This is an aerial image from Google Earth. You see at the top, this is our problem site A. It is at the cul-de-sac of Marie Street, or Marie Drive. This is our problem site C. It's the entire ephemeral stream that runs through the Greenbelt area. And by ephemeral, I mean it only fills up during storm events. So there may be water like in the stream, but there's no flow. And here is our problem site C. After speaking with the Homeowners Association, we decided to go with the low-cost solution. And so our low-cost solution for this problem site C was just to do nothing, leave it alone. We'll get into that a little bit later, but for our project, for site A, here at the East Marie Drive, there's a swale, a grass-lined swale, as you can see from the image next to it. Whenever storm events happen, it becomes really flooded, and due to the grading of the swell after the inlet, the water gets stuck there. Moving on to site B, it's from top to bottom, it's 1,700 feet long. As I just said, it's an ephemeral stream, and there's 3 major inlets to the stream, and they come in from site C right here. They come through site A to here, and then this cul-de-sac also inlets into the ephemeral stream. This is just some of the main problems we see at problem site C, or at site B. This is a giant hole just kind of right towards about 300 feet from the bottom of the top. But it's constantly full of water, and as you can see on the right image, it's starting to cause a pretty large problem. Here's the area at site C. It's already got riprap on it, and other than small rocks being taken away, it's still in really good shape, so we didn't want to damage the structure and the rooting system that was already there. So we just decided to leave it as is. Just for a third-party involvement, Parkview Estates asked us to see if there's any way that we could get the City of Stillwater to help out with some of the cost sharing. And this is a manhole that is just to the left of the Site C outlet. And as you can see, the ephemeral stream is starting to erode around it, so we would like to be able to get something done there and hope that the City of Stillwater could help with that. And as far as for sources of the flooding, this is an image of the original site plan of Parkview Estates. It was designed in the early 70s. And as you can see from the quadrants, they designed this neighborhood in pieces. So as for like problem site C, it was made in the zone 2, and everything, it was designed for that flood, for that type of drainage situation. And so everything that's been built above it over the last 50 years is going through that same drainage system, and that's why we're seeing a lot of flooding occur. There's also a problem in Site B. It's basically a barren stream. There's not really a lot of vegetative cover, which is why the sheet erosion is happening and the cutting at the problem Site B that you just saw. Also, the soil type of the neighborhood is a major concern. They're just mostly clay, and after soil testing, waited for a couple hours and it didn't drop at all, the levels. And for our watershed delineation, we decided to use stream stats. And we did that so we could find the contributing area of the watershed to our outlet at Site B. And after that, we decided to do ground truthing to make sure that our data was, the data we collected was correct. And so that image in the middle is what our final product of our contributing watershed was. And to the right of that is our Google Earth we made subreaches using Google Earth Pro, and we used the sub areas to determine individual
areas for water flow. Okay, here's some more background and research. To determine the cross sections of the stream and the site A, we use laser levels and measuring rods and 300-meter tape. What we would do is lay the tapes out and get points along a perpendicular cross section of the stream, probably around 5 feet each. That gives us a nice view of what that individual cross section looks like. This data helps in the design of Site A and Site B. When determining the soil, we used a ribbon method. This is a method by the NRCS, Natural Resource Conservation Service, formerly known as the Soil Conservation Service. This method is a touch and observation feel method that you take the soil, rub it in your fingers, as you can see on the right, until it makes a ribbon. And then once that ribbon breaks, you can measure it, and that will tell you a soil type. You can do the feel is by rubbing the soil in your hand, and by a level of grittiness, that will give you a soil texture. These methods were used to determine the soil types and texture. As you can see in this last picture, we took a soil probe, and we got about almost a foot of clay at the topsoil. So, more background and research. At the beginning, we were trying to implement low-impact development by use of a bioretention cell, rainwater harvesting at individual houses, and permeable fields in some of the culverts. Due to some budgets and feasibility of it, we decided not to go with the low-impact development, but more simple designs. And we will get to that later in the future expansions.
Okay, so now we're going to start talking about what our final designs are for our project. So we're going to start with problem site A. Now there are two main problems at this location, the first of which being the ponding in the cul-de-sac area. And the main reason that we are seeing ponding in this particular cul-de-sac is the poorly sloped waterway that it is supposed to exit at. It's at a pretty bad slope, about 1.8%. And also the design of that particular water exit, it just is not able to handle very much water. The second problem we see at the site is erosion. Now once the water does reach the end of the waterway, it travels down a greenbelt area until it enters the stream. Now in the greenbelt area, there are several obstructions that are in the path of the water. And once the water reaches there, it just erodes around it. And you can see that picture of the stump that's in the middle of the waterway. The water has just continued to make that deeper and wider. And so there's several of these sites located at Site A. So from the map area, this is an image that we developed. It shows the directions of the water flow at different locations in the neighborhood. And so we were able to use topographical maps and ground proofing to go out and just see what direction the water would go at certain streets. So this was really valuable to us because it helped us to determine how much of our areas could be subdivided into sub-reaches. And so the area in purple, around right there, is the area at problem site A. And so there's a pretty good amount of area that's contributing to this watershed. So we were able to use this information to develop solutions. Now the original design for problem site A has a very small drain and it leads into a 4-inch diameter pipe. This pipe is extremely undersized for the amount of water that comes to that cul-de-sac. And so on top of that, the pipe is broken. Yeah. So the broken pipe area has a large eroded spot around it. This is bad. For one thing, the erosion is continuing to expand. We started in August, and we can go back and there's an obvious difference in how much area has been eroded at this spot. And on top of this, it's a common entry point to the greenbelt area where there's a pool and playground. And so this is definitely a high priority site for us. Another problem at the design of this outlet is the fact that the soil and the grass level is raised above where the water can actually drain into it. And so what will happen is that it'll build up, it'll go through that pipe, but not fast enough. And so it'll eventually back up into the cul-de-sac, and it's potentially causing problems in a driveway at a residence home there. So when we were thinking about solutions to this particular site, we knew that we had to prioritize getting the slope of that waterway corrected. Like I said, right now, it's about 1.8%. So for our final design, we wanted to change that to a 4% slope. Currently, the 1.8% slope travels to about 120 feet in length. At that point, there's a hill at almost 10%, and the hill helps to guide the water to where it needs to go, eventually to the stream. So for our final design, the 4% slope will continue until about 150 feet, and then it will exit near the end of the hill and be able to travel to the stream much more efficiently without causing ponding in the cul-de-sac. These are images that we were able to develop using AutoCAD software. We took measurements from these sites and were able to input that data into AutoCAD. And so we took the current swale and we were able to use our designs and edit that in the AutoCAD to make the final design of that swale that you see. So a little bit about the mathematics and the hydrology behind this. We first had to determine our time of concentration of the sub-watershed, that purple area. The time of concentration is the amount of time it takes from the water at the very edge of that watershed to reach the exit point. There was a couple of assumptions we had to make when finding our time of concentration. And the first thing we had to consider is the fact that the path of the water is not a straight line. A lot of times the path of water is determined by the slope of the land. So if you have just an open field or an area like that, many times the path of the water is linear. However, with Parkview Estates, the design of the stormwater system is through the streets. And so there's no underground piping system that the water is directed to. It's actually all on the surface. And so the houses and the yards and the driveway, it's designed to put all of the water into the street, and the street is the conveyance system. And so we had to take the length of the furthest street to the outlet in order to get our time of concentration. And this was just one of the assumptions we had to make because it was an urbanized area. So once we found our time of concentration, we decided to go ahead and find our rainfall intensity for that area. Rainfall intensity is just the amount of water that comes down at a certain time rate. And so we based this intensity on a 100-year, 24-hour storm. This was chosen because the city of Stillwater designs their stormwater systems with a 100-year, 24-hour storm, which is basically a storm that you would expect to see every 100 years. It's very large. And so we wanted to see if we could match this design parameter with our own project. So we determined our time of concentration. We went to the ODOT roadway and drainage manual. We're able to find the rainfall intensity from an IDF curve there. Once we found that, we wanted to determine what our maximum flow at problem site A would be. And so that's the peak flow, which we use the rational method for that. That's the second equation you see there. And finally, to determine if our channel was capable of handling the peak flow, we applied Manning's equation to the swale, which is that bottom equation. So the peak flow we determined was about 35 cubic feet per second of water. As you can see, we multiplied our intensity, 10.5 inches per hour, multiplied that by the area of the contributing watershed, 8.24 acres, and then that 0.4 is our runoff coefficient. That basically indicates that asphalt is the avenue of the water to get to the outlet point. So yeah, it's hard to imagine 35 cubic feet of anything coming at you. So we were not really sure if our design would be able to handle that much water. You know, maybe we might have had to downgrade to a 50-year storm or a 25-year storm. So we applied Manning's equation to our swale, and we cut it up into 14 different cross sections. And so we applied Manning's equation at each cross section, we summed them and took the average. And what we found is that if we take just the added swale that we want to put in, it will handle about 23.8 cubic feet per second of water. But the area around it, from house to house, including all the green space that it has to go to, that can handle 42.7 cubic feet per second of water. And so after these numbers, we were quite confident that, yeah, the swale is capable of handling a 100-year storm, given that condition. Here's a top view of the current swale compared to the new swale. The swale that we want to be constructed in this area, we want it to be parabolic in shape and really very smooth with the existing condition of the whale. It'll be about 12 feet wide, roughly 150 feet long at a 4% slope. After construction is completed, there will be about 6,000 cubic feet of soil removed from that site. And then there will be about 350 square feet of sod cover to place after that. The sod cover is extremely important because we really need to establish vegetation at this site in order for it to be successful. If there's no healthy vegetation, it will erode just like any other site. And this will also help to slow the water velocity as well if there's healthy Bermuda sod growing there at a fairly decent height. Here's another image of the swale. And as far as the greenbelt area goes, all of the obstructions that are in the waterway, they must be removed. That pipe must be removed, the stump and the other rocks in the area have to be taken away and regraded to the shape of the swale that's surrounding that area. So after the regrading, again, we need to put Bermuda sod down at those sites and allow the vegetation to grow. And so after all these changes have been made, we're pretty confident that this area won't be experiencing ponding in the cul-de-sac or erosion along the greenbelt area.
Okay, moving on to the final design, Site B. This is one of our high priority sites, the ones that we've mainly been focusing on. As you can see, there's severe erosion on both left and right side of the banks. This is caused by large volumes of stormwater coming into the stream, hitting these bare banks that have no vegetation on them and eroding the soil. What this site is experiencing is severe head cutting. This is when, and undercutting, and this is the terms used when erosion is affecting the bottom of the bank, and you're getting almost like a big U shape, and then the tops will start to fall. So far, when we started in August, this site has increased probably about 2-3 feet in width. The erosion is getting worse and worse. The pool there is about 6.5 feet deep, and the width of that stream, the width of the hole right now is 13 feet wide. So the location of this site is kind of southeast of North Williamsport. This is a little out of the way. There are other sections that are definitely more noticeable in the Greenbelt area, but this design can be applied to those as well. Some hydraulic facts about the site. Since it was a stream, we were able to use stream stats and get a mean annual precipitation of around 37 inches per year. The drainage area is over 100 acres, draining all into this stream when it rains. The average daily flow is very little, and that's because the stream is ephemeral and it only fills up when it rains. And so after it stops raining, the flow is down to a trickle. The way we approach this problem, and since it is ephemeral, is to look at it as a gully more than a flowing stream. Some simple design went into this as we would measure the depths of the stream and the heights of the banks and take 2/3 of that value and then go horizontally outwards, and that's when you would begin to excavate the banks and make them into a more stable 45-degree slope. This will make a more healthy system for the stream and will allow vegetation to take hold. After the banks have been graded, Bermuda sod will be planted to help with erosion, and the big thing is the water that is standing there. Like I said, this pool is really deep. It all needs to be drained and filled with soil, compacted, and then covered with riprap. Now, riprap are large stones that are put in place of the stream along the banks, along the stream bed, that help to reduce erosion. But when the water comes in, high velocities, large volumes, it has a lot of energy behind it. And this riprap will slow that energy, decrease erosion. Here's an example of the riprap. Now, this is not us, this is a picture online, but it does has a great image of what it would look like. Once the water is drained, some soil put in and compacted, then you will begin to place large stones along the bottom of the bank and then work your way up with smaller stones until the top. So all of the soils is basically covered, and therefore it'll decrease the chances of erosion and the whole soil washing away. Here are diagrams of the proposed design. This is to help you picture it. Now, this is a perpendicular cross section. You'll be looking at the stream head on with it cut in half. The slope, the bank on the left is a little bit not as tall and steep as the bank on the right, but a 6.5 foot depth of water in this small gully is pretty severe. As you can see, the stones on the bottom, that will be where the riprap is placed. Here is another one to help you picture it. The water will be flowing this way and leaving this way. This is a horizontal cross section. You can see, again, the soil will be excavated to make a 45-degree bank slope, and then the riprap will be added along that inlet. So when the storm water comes in, it'll hit that water and dissipate the energy, reducing erosion. Here is what the aerial photo will look like. Starting up on the left side, working our way right, you will see the green area. That is the Bermuda grass that is to be added on the 45-degree slopes. We have smaller stones working our way through the middle toward the larger stones. And this whole place will be lined with riprap after excavation. And you can see how wide it is now. It will be wider afterwards, but it will be a stable and healthy environment. So this is where it comes down to cost. For the entire project, both site A and B, we're looking at around $6,500 to $7,100. After contacting previous excavation companies, we were informed that the site is very small and that they wouldn't consider working on this. They referred landscapers. So we took it upon ourselves to just go ahead and do some of the landscaping calculations. Using local price estimates from, say, Canutton Rental, $600 per week for a skid steer and trailer. Now you're looking probably a little over a week's worth of work with a landscaping company. That'd probably be about $4,000 to $5,000 a labor. The turf for 450 square feet. This would be to cover site A and site B around $1,000. The riprap just for site B would be around $500.
All right, and then talking about some of those future expansions that could be added to some of these sites. We still would really like to see some LID implemented in this area. The main issue is the soils are so full of clay that the water can't really infiltrate very well. So any LID we implemented would have to be enhanced. So starting here with our enhanced bioswale, we could add this to the current swale that's already there. We would just have to go through and take out a layer of topsoil and replace that with a more permeable soil, such as a sand, some, asphalt aggregate included possibly in that area to help infiltrate the water, so we're not pushing as much water straight through that area and getting some of it down into the soil and reducing kind of the surface runoff, as well as permeable pavement. We're in a neighborhood, so obviously there's going to be a ton of concrete in the area. All of that being an impermeable surface, you're just pushing all of that water to the green space. Permeable pavement could be a very great application in helping to reduce the surface runoff as well, allowing the water to infiltrate into potentially, like in this diagram, an under drain where it didn't have to run across the surface and cause as much erosion. Another LID practice we would potentially like to see implemented would be a bioretention cell. So here, this top picture is at the very bottom of the hill at East Marine, kind of a meeting point for several flows. And then over in this right-hand picture is down before the water enters the stream. At the bottom of East Marie, we believe that anywhere upstream from this area would be a great place for a bioretention cell. You have several different inlet flows coming together. It'd be a great place to kind of slow the water down, allow it to infiltrate. This would also improve the water quality reaching the stream, helping to kind of clean out the soils, or clean out the contaminants from the soil before it gets to the water. Moving into Site B, as you can see in these pictures here, there are several places where the banks are still pretty sheer. As a future expansion, we'd like to see the entire length of the stream reshaped to kind of get that nice 45-degree angle to reduce kind of the head cutting and undercutting erosions. As well as the riparian zone. In the time that we've been out there, we have noticed a very concerted effort from the homeowners in kind of leaving a no-mow zone on either side of the banks of the stream. And we'd like to see that continue. The riparian zone really helps kind of hold in the banks and slow down the water before it gets to the stream. It has to go through taller grass with longer roots before it can kind of tear up the soils around there. So that riparian zone is very important in helping keep the stream together. A few other things that could be implemented within the stream itself. One rock dams, that would be like one rock tall. Could help if there's a place where the water is moving too fast and causing erosion. This would be a good place to kind of break up that flow and kind of cut down on the energy that the water is carrying, having to go through these rocks. As well as log and fabric stepfalls, areas where the water is kind of cascading down and causing erosion into a pool. This log and fabric stepfall would give the water would have to hit the logs before it could hit the soil, potentially, breaking up the energy and reducing the erosion in those areas. Moving into Site C, this was an area that we decided to kind of leave out for cost benefit. That being said, if they were to kind of address this area later on, we'd like to see larger riprap added. As you can see, because of this large outlet, some of this riprap has washed away, potentially because it was undersized. We'd like to see a little bit bigger, a little bit better riprap implemented in this area. And then the area, as well as sodded, we'd like to see more vegetation in this area, help hold the soils in so that it's not eroding away. As well as potential regrading. If you look downstream, it kind of bottlenecks in. We'd like the water to be allowed to spread out a little more so it's not hitting the stream with as much velocity, having to go through kind of a smaller inlet with the large amount of water that comes through this outlet. We'd like to just take a few seconds to say thank you to a few people. Dr. Weckler has been fantastic this year working with us, putting up with us, more like, but. And then Dr. Vogel, he's been very helpful. He's kind of our specialist guy. Anytime we have a very particular question we need, Dr. Vogel is always there for us. And then, of course, the Parkview Estates Homeowners Association and residents, many of which are here today, have been very hospitable to us, been very helpful with us, anything we needed while we were there or anything we've had. They've been really great for us. And then, questions? Let's get
Where to start?
I think in Site B, we were talking about putting the riprap into that one section and bringing in soil. Would you recommend using? We know that clay is horrible for that area already. Would you recommend bringing in a different type of soil to go with the riprap, or using the existing clay that's there and maybe taking it out of other areas using that?
What would probably happen is the soil that was excavated at Site A, or even the soil around the banks, would definitely just be reused again.
Okay.
The same cost. Yeah. Yes, Dr. Vogel.
Question on that site right there, so as that's rebuilt, you're gonna still have a little pool after the storm. So did you guys think about, is that gonna be an issue if you have water sitting in that gully area for an extended period of time after the storm? obviously there is now, but even after the page, you'll still have that there.
It won't be as severe. The pool will be very small. The elevation on the inlet side where the water is coming in will be higher, built up higher than the when leaving the leaving side outlet of the rock. So water will be there. It won't be a huge, dangerous pool as it is now. It'll be a rock pool, and the water will either evaporate or trickle down.
Did I see correctly that the depth limit is 6 feet, that hole that you measured?
Yes, I tried to do some surveying in there. It's pretty difficult.
The current depth is 6 feet.
What
We're-
safety features you have for kids that are playing in there with the ball?
Currently, there are none.
The current hole is 6 feet, but the new design one will be raised above that. It won't be that deep.
Yes, sorry. Okay.
One question, riprap size, did you do any calculations on velocity and what kind of riprap, or what size of riprap you need for the various sizes that you were referencing?
No calculations of the rubber. Just a basis of larger stone, medium-sized stone, and smaller stone.
There should be some guidelines that we took from a study, I think from the NRCS, about riprap sizing for this stream. Should be in the report.
Did you talk to the homeowner association about their mowing equipment and what slopes that they can use that are best for their mowing equipment? I think you're showing one slopes, and did you talk to them at all about that?
No, not the maintenance. The only part of we talked to the homeowner association and maintenance landscaping is the riparian zone, which I say is working great. Since August, it's been dead grass for quite a while during the winter season, but now that the riparian vegetation is coming up, we're already starting to see a lot of vegetation come back on bare spots that we didn't think that would happen, and it's working great so far.
We do know that lawn mowers, their maximum slope that they really should be able to handle is about 5 to 1, horizontal to vertical. And the banks of the stream will be about 45 degrees, but there shouldn't be any mowers at that particular, at the bank of the slope. If they wanted to weed eat occasionally to kind of help the vegetation not get too out of control, that'd be fine, but mowing probably won't be happening.
You talked about the max channel flow on site A, I believe, swale, and you mentioned that you averaged the flows through that, you averaged all the flows throughout those cross sections. Why did you use the average and not the minimum or most limiting flow to calculate your maximum flow?
Well, I think in that case, it was just be able to give, there's a high range that we go to, there's a low range that we go to, and the average I just felt comfortable putting it in the middle.
I have a question. The vegetation that we are now letting grow on the sides of the banks, how high can that, if we were to weed eat like the tops of it off so that it doesn't really become, how high should it be if, it's tall?
As long as it's not mowed directly down, as long as I would say about a foot. And you want these plants and the vegetation around the stream to be healthy. And the long roots holding all the soil together. That's the main part.
Right.
So bare grass that's been cut is not like that. That's the root.
I think on side A, you had some numbers of 5,000 to 6,000 cubic feet of soil being moved. Where is that being moved to? Is that being used at some other site?
Some would most likely be excavated and used at the site B for packing down that large hole, but the rest would just be.
We'd use the rest to fill in any of these holes, like the stump hole would be filled with this dirt. After the pipe was removed, that would be filled back in, because I'm not sure the pipe's necessarily part of our swale. Just those kind of areas. Any
Much
areas
of
where
it will need to be removed off-site.
Paul, since we have a lot of customers here, Mount Stillwater out there, kind of by Walmart on 6th Street, back over there. When we did the stream restoration site, they moved a lot of the soil over there, and that developer would take soil from other folks.
Will he supply the dump truck? Something to add to your budget, dump truck.
Thank you. Anything else? Anyone?
Any other questions for this group? If not, well,
Did the city indicate any interest in participating in the project?
Yeah, there's a possibility of that. We did hear that there is a possibility of that. The homeowner association will have to coordinate with Charter Labs and other city planners. And yeah, it's possible.
Maybe I missed it, but what was your plan for the exposed sewer manhole?
We currently don't have a plan for it. It was kind of a looping point to hopefully get City of Stillwater involved to help with a potential plan for that. That being their property, I guess.
Charlotte, can you answer it? What I would say is that the homeowners association in the city will meet, and we need to schedule a date, so.
I need to call them on.
okay, let's give this group a round of applause. And if you could fill out your evaluation sheets, I'll come around and just pass them one way or another and leave them there. I'll pick these up. We will have kind of an open house out of the laboratory for more question and answers, show and tell. You guys need that? Okay.
Your way.